Good morning, everyone. Oh, sorry, not good morning. It's good afternoon. Hello, everyone. Welcome back to another challenge day 50. 1 minute. I have to close the door. Well, day 50 of 75 ultra hard challenge. We have almost today we're gonna complete two-third part of our challenge actually. So this is gonna be interesting. My bad. Okay, so how are we all doing? Let's say we're doing great because there's no one watching here right now, but it's fine. Today we are gonna actually start off with the second unit, current electricity, and complete it fully today itself, so that tomorrow we can start the other unit known as electrostatics. So what are we gonna do exactly is that we are gonna first complete this one part of the physics chapter, and we have to fully focus and we have to do this very nicely. All right, so today's focus is only on physics, no other focus. We are not going to do any other work. Like, yesterday we were also doing mathematics, but now we are not going to do that. In this case, we're going to apply another method. Okay, we are not going to actually do any other stuff. We're going to only do physics. So let's say that today is physics day, and here um I mean, let's say I'm gonna do it. I'm not sure whether you're gonna do it, because you're a kind of a person who may be free right now. You can do. You're just a person who have randomly stumbled upon me, and you're like, oh wait, like this guy is studying right now. That's crazy. Okay, but still, if I'm being honest, you do know that I was like kind of, you know, never mind. Oh, I did not know that I was doing this. Okay. So you do know that like the way I was literally, uh, studying, and yesterday was a crazy record. If you don't know, we were like studying like crazy. Alhamdulillah, that was because of God. And yeah, I was also a bit tired. I had to sleep because I slept very late, and in a small amount of time, only like 3 to 4 hours, which is pretty much slow and very low. So we shouldn't be doing this, guys. We should actually have good amount of sleep. I know, I didn't sleep well, but it's fine. Right now, I'm fine with this, and we have completed the assignment. There are only three questions which I have to complete for determinants, and then that's over. So that's one thing, and this should only take me about like 20 to 30 minutes, because those questions are not small and they are very big. That's what I've noticed. Another thing about this is that current electricity. So we don't need to focus on maths right now, because that's not the important case. Today we're gonna focus on physics, full physics. We'll start off with current electricity, and I'm not gonna speak much today because this is mainly based on the practice work. Biology was theoretical, so yeah, I didn't need to practice a lot, but um, that I was like referring to many notes like for a long amount of time. Plus, I was after the moment I just ended my stream, one person had it out, so I had to solve that person's doubt too. Let me just close that. So yeah, like that was one thing too. So overall, we're gonna start off with this second unit again, as I have already said, physics. Let's lock in, guys. Okay. So I'm gonna mute and study very carefully, because this is something which I really need to lock in for, and I have to be really careful because this subject is not easy at all. So it will take some time. Let's move on. Let's focus really nicely, and I'm not gonna talk much today in the stream. Like yesterday I was, but because physics was something which I'm very bit less prepared of. Uh, and biology was the thing that I was already prepared of, so I was able to like do it nicely. Biology exam was okay. It went great. It went great. Alhamdulillah, because of God. But I want to just focus for physics because I want to see if I can complete physics very well. So yeah, let's start off current electricity. I'm gonna put a timer. Do we need to put a timer? Let's try completing. Okay, so we're gonna divide each chapter on the basis of theory and laws, derivations, and numericals. So we'll try completing full theory and formulas in 2 to 3 hours. That's what I'm gonna do. And derivations will give another more time, and then numericals another more time. Because today we are only gonna complete current electricity. That's it. So yeah. So we're gonna give this 2 hours. And if you want to study along with me or do any work or you want to enjoy or anything, you're mostly welcome. Let's go. 2 hours. Yeah. So let me just do that. Three, two, one. I'm looking. The rate of flow of electric charge that takes place through any cross section of a conductor in a definite direction is known as electric current. Is equal to Q by T. Coulomb. Second. System any cross section of the conductor in a definite direction. The direction of flow of positive charge gives the direction of electric current and is called as conventional current, because electronic current, which is opposite to the conventional current, electric current. Okay, let's start off with our first dot. Okay, this is gonna be our first dot. I'll keep doing this every day. I think you guys got the screen already. Yes. Whenever I'll open Chrome, you'll see a screen automatically popping up. So that's one thing. Because I've set a mode, conventional electricity, electricity, and non-conventional. Okay, I will say electronic current. Wait, conventional. current. Okay, let's say current. My bad. Current. Yeah, it says this electron current. What is this? Electron current. Okay, so conventional current. All right. Electron current. That is the electron flow. Got it. Thank you very much. Let's do this, guys. The direction of electron. My bad. If anyone wants to say anything, I'll talk. For now, I'm just not gonna say anything right now because I'll be so locked in. I'm sorry, man. I mean, I don't know why I'm being sorry, but okay. Let's say. Current carrier should be electron according to me, but let's just check. Mm, okay, let's check this out. Free electrons. Okay then. Okay, okay. Free electrons. Yeah, that is more specific. That's true. Okay then. I'll write it here. Free electrons. Oh, my charger. Well, what is this? Get out. Yes. I'm not gonna be using a lot of laptop today, except for streaming. But yeah, I will try. For I'll try using my laptop only for doubt purposes. So that's one thing. Because while I will be studying for and practicing for physics, I'll have a lot of doubts coming up. So yeah, I have to be ready for that. Like I had a lot of doubts yesterday in biology. Now how I kept solving them. Like it wasn't me who solved it. It was I was using AI to solve it. That's one thing. And Google Gemini. Ouch, my leg. Here we go. Oh dang, I'm taking a lot of time for just some pages. But let's try. Let's try. I'm not gonna give up. It has only been like less than a half hour, so no problem. Uh, I don't know when I will be like sleeping at, but today we'll be working really hard today. drift velocity and what. Yeah, I was missing one point actually in the law statement. That's why I was searching for it. if you don't know. I was like searching. I forgot that there was one point that I didn't write it down, so I just wrote it here. Ohm's law is one of the most important laws. The current flowing through a conductor is directly proportional to the potential difference across the two ends of the circuit. Or circuit. How do you pronounce circuit? Is it circuit or circuit? I would call it a circuit. Provided the temperature and physical condition remains unchanged. So I'm gonna write temperature and physical conditions. Yeah, it feels like kind of dependent on AI, but I think it is still important to know that because even though AI can make mistakes, and I do know that, what I really have an idea is based on the fact that I can actually like still get the missed out points. So this is important. So yeah, I think I need some extra space. Like let's put this here because it's literally covering my laptop when I'm putting my book here. رب الفلق من شر ما خلق ومن شر غاسق إذا وقب ومن شر النفاثات في العقد ومن شر حاسد إذا حسد. I think there was no data for some reason. Okay. قل أعوذ برب الناس ملك الناس إله الناس من شر الوسواس الخناس الذي يوسوس في صدور الناس من الجنة والناس. The reason why I recited these both surahs is because I want to just be staying away from the evil eye. I believe that evil eye exists from people, and reciting these surahs, and according to our religion, reciting these surahs prevents, you know, evil eye. That's why I'm doing it. Because I feel like some people will put an evil eye, and I've noticed that. The current flowing through the conductor is directly proportional to the potential difference provided. The current flowing through the conductor is directly proportional to the potential difference across the ends of the circuit, provided that temperature and physical conditions remains unchanged. Right? Across the ends of a conductor. Okay, let's say that. What does the Gemini has to say about this? Ohm's law, right? Yeah. Cross it. Does not mention it, that's fine. I believe in my teacher, so I'm just gonna write conductor. V is directly proportional to I. When we remove this, we get V is equal to IR formula. Nature of material, temperature, and metals. Dimensions. Yeah. You know what makes me feel weird about those constants of proportionality or any constant is that they still vary. There are some constants which are universal, like the universal gravitational constant, universal gaseous constant, which are just having the same values, of course. But then there are so many constants like the equilibrium constant or the Henry's constant, or not only those, but there are many constants that we have learned across in science that have a lots of variation. And it says that resistance is also a constant, which I do agree in this case, because if you look at many cases of when you're finding the voltage, the current, and then you're checking the resistance, you see that the resistance is literally constant. So yeah, that's fine. But then the constant literally varies here. Resistant varies because of the nature of material, the temperature, and the dimensions. Nature of material, because I feel like because of the distance between the molecules or anything like that, or the free electrons, the amount it possesses, like these conductors or those insulators or those semiconductors or any type which are exhibiting these types of resistance. Like I think every conductor has every material has some amount of resistance, even though if it could be that large or negligible. So that's one thing. Then temperature, of course, resistance is dependent on temperature. If we increase the temperature, resistance also increases in case of metallic conductions. But in chemistry, you studied that there was electrolytic conduction, where when we increase the temperature, the dissociation takes place, where ions are formed, and these ions are the current carriers of the current. So in electrolytic conduction, so there it actually increases. I mean, not the resistance, the current flow increases, so resistance decreases in that case. So those constants vary, which makes me feel wonder, like, are we even calling constants at a point? That makes me feel so weird. But now I know why, because it's constant of proportionality. But it's so weird when you're seeing constants literally varying a lot. So that's one thing. Oh yeah, what else? Rheostat, ammeter, battery, specific resistance. We are gonna move on to electrical resistivity. Now since Voltage and current are directly proportional to each other. Their graph is a literal upward slanting slope. So yeah, that is the graph where the slope gives r. I'm literally trying my best to not mess this up, guys. We got this switch K meter. I saw that there was one viewer actually. There was one viewer watching me. I did notice that. Then battery. No, I noticed one thing from my overall journey of learning PCMB. Every subject is really fun to learn, and I'm really grateful that I chose this stream. Trust me, even though this stream is really tough, I do agree with that, and you have to struggle a lot. I did notice that this stream is really fun. Like for me, according to me, okay, because I love each and every subject that I study. Like I even love English, studying English. It's just that I need to give enough time. That's it. Like physics, chemistry, maths, biology, English, every subject is just something which I really love to study about. So I don't lose my interest easily like this, studying this. But in 10th standard, I had some subjects which I didn't have that much interest. Like, I did have a lot of interest in science and maths in 10th. And I do remember that I had a less interest in social. No, I really had some interest in social, but not much as science and maths. I did have some amount of interest in English. That's why I was able to ace good in English actually, and along with science and maths in boards. Then Hindi. Yeah, Hindi was the one which I had least interest in. I shouldn't have done that though, because Hindi is something which is really important for me to learn during that time. It was very crucial for me right now. And if you look at it, English, science, and maths are those three subjects which I'm studying right now in the stream. Like science is basically physics, chemistry, and biology, and then maths is maths, English is English. So I'm having all those five subjects all together. One thing. Okay, we have the rheostat, we have the key which is open, we have the ammeter. Okay, this one. This is the voltmeter, connected parallel. So ammeter minus plus. Wait, how do you represent this? I have a doubt. Wait. Representation of electric circuit. I want to know about the signs that they use for uh, with ammeter and voltmeter. Let's check any image. Let's check the images. Wait, we need to use the images for this. Hmm. Give me those with the yeah. I need this one. I needed the signs. Like this is plus, this is minus. Where does this move, by the way? This will move from here, 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 here. I need to show the current direction. Yeah, okay. And then ammeter. Actually, ammeter wasn't supposed to be there. It should be there on this side, but okay, it's fine. Now here, since the positive, this is positive, this is negative because current is coming from there. That's why. And here it's like positive, and this is negative because the current is still coming from here. So that's one thing. Alright, got it. So whenever current comes, we need to show that positive direction, but for the cell, it's literally like the from the positive part of the positive terminal of the cell, the current will move from on from the like from there. But you know, current will move towards the positive terminal of voltmeter and ammeter. That's what I know for sure. Okay, got it. So that's one thing I wanted to know. a rheostat, ammeter, and voltmeter. I know I'm taking a lot of time, but trust me, this is very worth it. I know for that for sure. Electrical resistivity. I feel like we are doing great, guys. I'm just skipping derivations right now because we have to first complete the theory part. Then we'll move on to derivations. This is going to be a three-step process for each chapter. Electrical resistivity. If we get enough time for today, then we can even start electrostatics because we don't need to waste time. Electrical resistivity. If we get enough time, but I don't think so about because usually that doesn't happen. A specific electric resistance. You know what? Electric. Oh, okay, it's true. Resistance of a conductor is proportional to length L. Okay, this one, I'll just say that. Even though this is a kind of a derivation, it is not. It's just a theory part. The problem. Okay, never mind. Let's just do it. To length L, and resistance of a conductor is directly proportional to length L and inversely proportional to area of cross section A. Area of cross section, capital A. Okay. R directly proportional to L, first equation. R inversely proportional to A, second equation. From to combine 2 and 1, so 2 and 1 together will be giving me R directly proportional to L by A, and applying the proportionality constant, we get specific electric resistance, or known as electrical resistivity. So proportionality constant. Proportionality constant. Electrical resistivity of a wire. Resistivity of a material, let's say. Because this is mainly to know the resistance, specific resistance of a material. That's why. Okay. Um. You know what? What are we doing, y'all? In the derivations of Ohm's law, why did we prove? Okay. Oh yeah. Wait, what? You can literally say that V by I. Okay, I have to check the derivation once. I don't know why I got confused here. V by I is equal to R. Because this overall is resistance, and resistivity is mne squared tau, where m is mass, n is, I hope so, it's mass, right? Yeah, mass. N is number of electrons, E is the basic unit value of charge, and tau is the relaxation time. I like that name. I like that term, relaxation time. Oh man, let me relax. I like that name. I don't know who put that term. Okay, so okay. So there is a formula that we study in this Ohm's law that is seen in derivations. So that's one thing. ml by n a e squared tau, where m. So let's say that this is third equation, m by, yeah, this is the third equation that I'm going to be using, by n e squared tau into L by A is the fourth equation. So from 3 and 4, after we complete resistivity's dependency, I mean, okay, before completing that part, we will have to revise it again, just for a quick recap. Then we have some numericals here. Okay, then we have variation. I have to check this out because we need to keep checking this out. Ohmic and non-ohmic devices, current density, superconductivity. These topics are easy and fun, so we can do it, I feel. Then we have some derivations to deal with. Yeah, after that, after some derivations, we have like EMF, DPD, and internal resistance of a cell. This one is again a derivation thingy. So yeah, there are a lot of derivations. I mean, of course, so we have to deal with that. And then Kirchhoff's law. Oh no, wait a minute. Let me ask a person. Let me. Uh, I need to actually ask for help because I have one part missing up, so that I can use it up. Like what else? Clear all here. Yes, clear the search history and then move this like the WhatsApp search history and then what was it? After the topic of parallel Kirchhoff's law, right? So this is hmm, what else? Okay. Hmm. Oh man, need to get enough time for numericals. That's one thing about that. Hello, I'm gonna ask one of my friends to send me one note part because I was absent on that day. Because one of my friends have a really good way of writing notes, so I'm gonna ask him. Uh, and it's my friend's other friend's recommendations to ask him too because he says that they say that his notes are really good. He writes really fast and in a neat way. So I'm gonna ask him because mostly I will never ask him about this. But some yeah, I have asked him about this in once, and yeah, it kind of helped me out if I'm being honest. So we're gonna use that to also write down. I'm not sure it's WhatsApp, so I'm not gonna share it again because I don't want any risk to leak a number. If I leak a number, I'm cooked. That's why. Like I have to delete the whole stream then. It's not because of the I have a worry of deleting my stream. It's because if anyone's number gets leaked, like just imagine about the trollings that they would get from the public. That's why. Even though I'm not a big YouTuber or anything, but still, this is a really big risk. Okay. Okay. So ML by NAE squared tau, right? That's the overall formula I need to memorize for now because we haven't done the derivation yet. So we get rho as m by n e squared tau. It depends on what all things. Let's check that out. Rho depends on material of conductor. All right. We are gonna master each and every chapter nicely, even though it will not be that easy to master. Or let's say we are gonna make it good and strong. Doesn't depend. It does. It depends on relaxation time and what else? Number density of electrons. Yeah, I don't know why I said n as an electrons. Wait, so n wasn't introduced in the previous ones, right? That's far as I know. Yeah, in the first derivation between the relation between the different drift velocity and electric current, number density was introduced there, but we didn't use it much. So that's one thing. Material of conductor, and then 1 minute. Yeah. Never mind. Let's move on. Doesn't depend upon dimensions, but it depends upon the number density of electrons n, or just say number of electrons because we just call it as a number. Number density of electron doesn't have any unit, even though it's kind of a physical quantity, which is interesting. Um, I mean, even though in units and dimensions we study about this, or units and measurements we have studied about it, it's still interesting to know about that. Relaxation time is also there. So yeah, I think these are the ones which it depends upon. Technically, like even though it's given here, right? It is inversely proportional to this, because okay, so the overall formulas that we have studied right now, let's just write them all out here, and then so we studied I is equal to NAEVD. We studied VD is equal to um, U average minus EE by M. So that is one. So Vd is equal to E tau by m. That's one thing I'm gonna use for studying. Okay, so E tau, E small e capital E tau by m. Now this small e is a representation of charge. That's what I know for sure. Now I'm gonna take this one out, so it's as it is not needed. So we got drift velocity, we got the current, then mobility. Mobility is basically E tau by m, because it's basically the ratio of drift velocity and electric field applied. So E tau by m. Then am I missing anything? Yes, resistance. It's equal to Vi. Sorry, V is equal to IR, and resistance is equal to ML by NAE square tau, and rho overall is okay. Thank you for 4 views, guys. Thank you very much. Wow. Uh, Alhamdulillah. M by NE square tau. M by NE square tau. Okay. I think we have studied these many formulas. What do you say? Am I missing anything? Yeah, E is equal to V by L is the formula which we study in electrostatics. So I'm not gonna include it here. But yes, E is equal to V by L is studied in electrostatics. That's what I know for sure. Like in the second chapter of electrostatics. So it's not a big deal here, but yeah, we needed to know that. Now we're gonna have a small quick go through so that we don't miss anything. So current electricity, this is a part where we start studying about charges moving in motion. So if charges are in motion, which means that they will exhibit both electric field and magnetic field in this case. And the rate of flow of electric charge, and now we start about discussing about these some new physical quantities that we come across. The chapter name itself is known as current electricity. So current is the word used here, and that current, which means that we are going to study about current, which is a physical quantity. Now current being the rate of flow of charge can be written in the form of Q by T, which is coulomb per second, or we can write the unit as amperes. And talking about current, it is actually of two types: the conventional current and the electron current. If the direction also wait, if we talk about a smooth way of writing saying electric current, it is the flow of an electric charge in a definite direction in through any cross section. That is one such type of way you can actually mention about it. Then talking about this direction of electron current and conventional current, the like let's I know I'm kind of stuck in here, but let's say this: the positive charge moving along with the electric current, I guess, let's say that. Yeah, okay. Yeah, the flow of positive charge gives the direction of electric current, called conventional electricity or conventional current. And the direction of electrons would give us, or the flow of electrons moving in that direction, is known as the electron current. Now electron current, or we call it as electronic current too, I guess so. And then electronic current and conventional current are opposite in direction. That's one thing we studied about this. Then conductors, they have free electrons. These free electrons undergo thermal velocity of 10 raised to 5 meter per second to 10 raised to 6 meter per second. But if we look at their motion, they exhibit a random motion, which means that they move in random directions. Thus their average thermal velocity will be zero, because they might form closed paths, which can actually give a total displacement at zero. And then that's why that's one reason for thermal velocity to be zero, I guess. Then when electric field is applied, the electrons will move will experience that force and will move in opposite direction to that of the electric field direction. Well, it will move from the opposite to that of the electric field direction. Thus, it gets drifted into that direction that is moving, and the velocity with which it gets drifted and it moves is known as drift velocity. And then this drift velocity is the one we have derived overall. It lasts for a short time, as it is interrupted by, yeah. Now if you talk about acceleration, acceleration is one such main key role here, because it happens for a very short amount of time, because electrons move very fast in a very small amount of time, so their velocity is very high. And as we can see from the thermal velocities, like their specific thermal velocities, like I'm not sure whether you can call it a specific, but their thermal velocities were varying from 10 raised to 5 to 10 raised to 6 meter per second, which is pretty much a large number. And then like you can talk about their acceleration, which is lasting for a short period of time and gets interrupted by those effective collisions or any type of collisions. Let's not say effective collisions, like there could be any kind of collisions that it's taking place. They can even collide side by side or head on, or any type of collision. It can be small, or it can be no, I'm not sure whether they can call it slow, because electrons glide in such a way that they move so fast, so it could be a stronger collision. And the successive intervals between two effective collisions, the time interval between the two successive collisions is known as relaxation time, and it is represented by the Greek letter known as tau. Is tau a Greek letter? How do we write tau, by the way? I think, yeah, I mean, I'm not sure if tau is a Greek letter. Maybe, yeah. And then what else? What else? Yeah. So tau basically acts as time. We can just say that. But in this case, acceleration is very short, so we're gonna get a specific time for that itself. So it's relaxation time. And if anyone wants to know what is the thermal drift velocity, so they need to actually like add up along with the thermal velocity, because thermal velocity is also there. But if we need to get the drift velocity, we need the overall thermal velocity and the overall other types of factors in which the velocity is taking place. So from this we get to know that thermal velocity's average is 0, so no effect of thermal velocity here. And with the drift velocity, so we should remember that drift velocity and thermal velocity is different in this case. And drift velocity is equal to a vd vector is equal to a vector tau. So tau is the relaxation time, and if we expand a vector, it will be minus e capital E vector by m into tau, and that is what we are getting. If we take the magnitude, we get e capital E tau by m for vd. Mobility is the ratio of the of the uh, what am I saying? It is the ratio of the drift velocity of the current carrier of the conductors, which is basically free electrons moving up, moving in the opposite direction of electric fields. I mean, which means, and the electric field applied in a direction, in a definite direction. I don't know what just seen said in textbook. Yeah, in an applied electric field direction. I mean, technically, the way I wrote the I said the statement is also correct. So that's also no problem. Then mobility also has its own formula. Mobility is equal to Vd by E, and we are just taking the magnitudes, not the vector forms. So Vd is basically small e capital E tau by m divided by capital E. Like E gets cancelled out, which means electric field has no effect here for the mobility. So it will be small e tau by m. And then Ohm's law. Yeah, before that, relation between drift velocity and electric current. This is one of the main first formulas that we study in 12th. But we don't do this in 10th, by the way. We didn't study about this. So I'm not gonna we have to study a derivation based on this, so I'm skipping it right now. So it will be I is equal to NAEVD. This E is small, N is the current density, A is the area of cross section, I believe. VD is the drift velocity. Then Ohm's law. The current flowing through the conductor is directly proportional to the potential difference across the end of the conductor, provided that the temperature and physical conditions remains unchanged. That's one thing. So V is directly proportional to I, or V is equal to IR, where R is the constant of proportionality, or known as the resistance of the conductor or resistance of the material. Resistance depends on the nature of the material, it depends on the dimensions, and it also depends on what there is one, yeah, temperature. It depends on temperature. Then talking about the graph of the Ohm's law, between, if you plotted a graph of volt and current, we get a straight line graph, like an upward graph, and the slope of that graph gives, of course, R, that is resistance of the material. Then writing down the circuit, we have the rheostat, the ammeter, the voltmeter, the ammeter connected in series, whereas the voltmeter connected in parallel. Bit, cut out here. Oh shoot! 1 minute. Oh, okay. I was a bit confused here. That's why. Never mind. So it's something like this. No, we had done physics practical builds based on this. That's why I was thinking about it. Anyways, yeah. Then we have the batteries. Rheostat is the one which will vary the current and what else? Yeah, volt, voltage, potential difference. Therefore, the resistance will still remain same because the current and the potential difference will either increase together or they will decrease together. That's one thing. Uh, then what else? Yeah, about their signs. This I need to know their signs too. For ammeter or like the battery, the current will move from the positive terminal to the negative terminal of the battery. The reason is drift velocity this time, not about the attractions of the charges here. That's why. That's what I've learned overall from this concept. Then another thing that I have to talk about here is the say signs of the ammeter and voltmeter. Ammeter's positive terminal will be towards current will move towards the positive terminal of ammeter, and for voltmeter is the same case, right? Yes. Yeah. I just want to check once again because I think the last time when I checked the circuit, it didn't show that the current direction consisting of an ammeter and a voltmeter. Let me just check the images. Okay, this is what I wanted. Okay, so this moves here towards. Okay, then. And that's the same case here. The current will vary here and here, but the voltage will remain same. Got it. Got it. Electrical resistivity, that's another one. Resistance of a conductor is basically directly proportional to, it depends on the dimension, so it is directly proportional to the length of the conductor and inversely proportional to the area of cross section of the conductor. So what happens is we can just write R is directly proportional to L by A, but there is a way you can actually write the constant of proportionality, and that is rho. This rho, which is this actually it is a letter, Greek letter again. I feel, I don't know man if it is a Greek letter, but yes, this letter rho represents the electrical resistivity. The electrical resistivity in which the rho represents is one such idea that we get about it. Then talking about the derivations which we have already skipped, we have skipped one derivation actually. We have skipped overall two derivations, and in that derivation we studied a formula of resistance, which is R is equal to ml by n e square a tau, and if we take the resistivity value from there, we get m by n e square tau. Okay. Talking about the electrical resistivity's dependence, it is dependent upon the material of the conductor or the material nature of the material. Let's not say material of the conductor. What if it could be an insulator? What if it could be a type of a semiconductor, or it could be any type of material in which it will vary. So that's one thing. Where was I? It could be dielectric too, but then dielectrics are really different. You know, dielectrics are different. It depends on the material of conductor, and doesn't depend on the dimensions, because we are saying that rho is equal to the resistance of a material having unit length and unit area of cross section. That's one thing. Then number density, yeah, depends on number density and relaxation time. We get to know that from the formula of rho is equal to m by n e squared. Now we'll start with where we left off. So rho is inversely proportional to 1 by tau, and rho is inversely proportional to number density. Because for the formula we get to know that. So resistivity is inversely proportional to number density of electrons, since the value of electron number of value of n depends upon the nature of material. Therefore, rho depends upon nature of material too. But, but this does not explain that right. What? Number density of electrons. It is inversely proportional because resistivity is inversely proportional to that. You're saying that. Okay, so this is not a clear reason. So we'll ask this to Gemini. Wait, we'll ask this to Gemini. Because it depends upon the nature of material. I want an even more clear reason for that. I know I'm kind of moving slow, but this is very deep method, man. The way I'm writing it down and studying is very deep, and I'm also revising the topic. That's why. But like this, we can literally strengthen our full chapter of current electricity. That's why. Inversely proportional to the number density of electrons, because it depends upon the nature of material. The problem with this is that the calculations we cannot reuse log for that, so I'm kind of sad based on it. Man. Okay, so let's say Y is resistivity. Can you guys even see that? Yeah. Let me just put my camera a bit down whenever I'm using it. Okay. Here we go. I'm gonna put my camera here. You can see what I'm writing now. Y is resistivity, inversely proportional. I didn't know that resistivity is inversely proportional to temperature. Technically, it should be right, but how does that affect resistivity? Because resistivity here. Okay, wait. Not sure about this one. Okay, let's just check this out once. Okay, this is a semiconductor concept, I guess. That's why. But let's not just check. Maybe. Why is resistivity? So that might not come, but still, we'll just know that for sure. Inversely proportional to number density. Number density. Why is it temperature, guys? Yo, what? Am I writing something wrong? Why is the search bar? More electrons means more available paths for current to flow, dividing the overall electrical burden. But that could be in the case of dividing it. Yes. So current depends on the current. Okay. Current depends on elective moment. So technically, you can say that electrical resistivity almost acts as same as the resistance, but here there are some things that may differ. Hmm, that's one thing I've noticed. Why is it for this one though? Oh, wait. The temperature topic is given here. Resistivity is inversely proportional to relaxation time because a relaxation time depends on temperature. When temperature increases, relaxation time decreases. Yeah, technically, kinetic energy is increased, so more collisions have a more chances to have. There are more chances to collision, so there will be less timing. So less relaxation time. But that doesn't mean that what? I'm actually confused. Wait, bro. If anyone writes that down, like I just saw that and I was like, wait, what? Not conductivity and temperature. Like I'm really confused in this case. Oh, okay. So it depends entirely on the material. So again, the moral of the story: resistivity always depends on material conductor. So it is like literally not obeying many of the dependencies. That's why, like number density and relaxation time. Okay, maybe we get it to uh, relaxation time because would lead to more collisions due to kinetic increased kinetic energy. We are using kinetic theory of gases here, I guess, due to more increased kinetic energy. But this is not gases. Kinetic energy, that's one thing. Kinetic energy. This, the relaxation time, resistivity, and temperature's relation depends on the nature material of the conductor. Depends on the nature of material. So that's one thing. When I studied this topic, it feels like I'm also like kind of studying of matter, which is basically chemistry too, you know. But that, yeah, of course, there's no such chemical changes going on here. That's true. Okay, so we have to study variation of electrical resistivity with temperature. Never mind, it's not there in this topic. We are studying it right now here in this. because okay, so 1 minute, I'm reading it out. So it says that in conductors, temperature would increase, where the vibrations would increase, and that will lead to more collisions. And okay, basically, I should have said more vibrations in this. Never mind. Collisions would increase, and that would decrease in relaxation time because this time interval between two successive collisions will be decreased, and then the electrical resistivity would increase that way because rho is inversely proportional to tau. Then, but increase in number of density is not considered in conductor. Now, what I feel is about this is that it is only dependent on the material, right? So that's one thing. For a semiconductor, temperature and okay, this is important because we have different cases for conductors, semiconductors. Okay, for semiconductors, temperature increases. Uh, the electrons would become free in that moment because when of excitation state of electrons, then the number density of free electrons will be increased then at that time, I guess. So that's what I would say. Okay, what is no mind. Okay, we'll write this down nicely, but we'll just check. Oh, I see. It says that alloys are some types of materials. If you don't know what alloys are, basically those are mixtures of metals. Some like bronze, or like brass, or what there was another one, amalgam. Yeah, these types of mixed alloys, they're mixtures. Like if I tell you about this, let's say zinc amalgam. Zinc amalgam consists of zinc and mercury, both. So that is one such type of way you can say that it is an alloy. Or constantan, yeah, constantan, manganese, nichrome, all are basically alloys. Wait, nichrome is an alloy, right? Just in case I want to know because well, who knows? I make mistake there. Is nichrome a conductor, insulator? No, it's not an insulator. Oh, look at that! It says an alloy. Yes, okay then. Thank you, Google. Okay, that was so fast. We are getting our doubts solved. Even though if it is very small, it should be solved. That's one thing. Okay, let's start. For conductors, temperature increases. That will lead to the vibrations to increase. That will lead to increase in the collisions. That would lead to the decrease of relaxation time. Relaxation time is decreased, therefore resistivity is increased. Here we say that resistivity is dependent. Yeah, increase in number density is not considered in conductors. Of is not considered in a conductor. Okay, sorry, in conductors. Having fun studying this because if I'm being honest, every subject is my favorite, but I had some different moods of styles. I had an enjoyment when I studied those subjects. Like Maths, yes, I do enjoy it studying. I do like practicing it. Then, of course, I also like studying biology because conceptual things are really good. But there are some other subjects which I enjoy more, like physics and chemistry. In fact, I enjoy more in physics because it's really interesting. You practice, you do derivations, you do that stuff and this, and yeah, it's something which is really interesting if I would be honest. So yeah, out of all, physics is my favorite. Second is chemistry. Third or it will be either maths or bio. Fourth will be either maths or bio. Fifth is English. I know English being my least favorite subject, but I like English too. Trust me. My English is a bit weak. I agree with that, but I really like studying English too. Like if it comes to English, so it's not a big problem for me. I just don't want any other external subjects like any other language to be learning right now because right now I like the stream. I like the way we are studying all these five subjects as the main subjects. Temperature increases, water density decreases, rho increases. Why does that? Oh! I don't because yeah, that's true. Temperature increases, number density increases, rho decreases. Okay, so that's one thing. In the case of relaxation time being increased in this uh, case, it isn't significant in semiconductors. Now, what I do know about semiconductors is that, there are not many free electrons actually. There are not many of them that would do those collisions or something. So, yeah, I do agree about that. But then, number density of electrons for this not being considered in conductors is a bit confusing for me. That's one thing. For alloys, increasing or decreasing in temperature, the temperature does not doesn't affect the resistance or resistivity. Really? 1 minute. Its resistance. I don't know. I can't trust my notes. Affected. Is resistance affected by the temperature in alloys? Yes, temperature affects the resistance. Oh, about resistivity? Maybe I will get some ideas. T witty. Okay, so okay. So there is an effect, but it is a negligible change. That's why we say it is unaffected. Manganese and Constantan are used as standard wires for standard wires which would act as a resistor. Okay, so we have another topic known as temperature dependence of electrical resistivity. I think this topic is a bit too deep. I did not notice that. My bad. So what we notice overall is that rho increases with temperature in the case of metals or conductors. So it will be like a curve. Will not be directly proportional because it could, or else it would have been this, but it is like an increasing curve. But in the case of alloys, the material has very less effect if the temperature is increased or decreased. And talking about semiconductors, rho is decreasing with temperature. Ohmic and non-ohmic devices. Okay, I want to talk about ohmic and non-ohmic devices too. So we have to learn the graphs, characteristic curve of diode. Now this is something which we need to like be really careful of. Okay, so after this we're gonna move on to conductivity. So we're gonna study conductance, which is G is equal to 1 by R, and then which is basically, or S is equal to 1 by R. And then we are going to study about conductivity. I don't know why in physics they represented conductivity as sigma, but which is this. But in chemistry they represented it as kappa or K, capital K. So I'm confused. Like, bro, can you just represent with the same letter? Why is there confusion with different letters? I've seen this with some different physical quantities. They have just different types of letters being used. Okay, maybe for different conductivities, okay, you might want to actually express that, but I don't think so. It would be great to express one just conductivity is general unit as sigma. Oh, thank you. We can have a good date now. Look, let me just close this up. Huh? Okay, so we have one, two, three, four, five, six breadsticks. I thought I had only two. My bad. Conductivity, superconductivity, advantages, and yeah. there will be some time taking. It will take some time for me to complete it. So after we complete till ohmic and non-ohmic devices, we'll revise the topic again. Fast revision this time because we don't need to waste more time. That's how I'm gonna do revision because this is apparently the case where I have to do it really fast. And if we get enough time today, we'll be also starting electrostatics right on the bat because tomorrow we need to get enough time to even do some extra work like a competitive exam work level physics because we need to be prepared as much as possible. And then for physics we have to practice like the paper that's one thing. So like there are two things which we have to do for physics. These are the two. These are the two things. But let's go. Let's go. So for alloys, increasing or decreasing the temperature doesn't affect the resistivity, or may have a negligible change though. Hello. He didn't even read the message. That's pretty weird. I hope he reads it. You know what? I'm gonna send this. Uh, let's go. Yeah. I will tell them. Take this out. I'll drink some water and come back because my throat looks a bit sore. Once I do that, I will come back. Okay. Plus, yeah, I have to pray. You know what? I'll also pray and come back because or else I'll become it will be late. Um, Till then, I'll just stop the timer because right now it won't actually matter much. So I'll stop the timer now. It's fine. So in the span of 2 hours, we did complete a bit of topic. It's fine. We didn't do much. It's fine. No problem. But but we are progressing. I'm happy about that. So yeah, rho is equal to rho naught 1 plus alpha delta t. Resistivity for delta t is t minus t naught. T for rho. That's one thing. Alpha temperature coefficient. That's why manganese and Constantan wires are those materials which are used to make standard wires as resistors. So that's why we use these two wires in physics practicals too. Yeah. That's how we can actually find this out. So this is gonna be something like this. So according to this, it's gonna be rho is equal to rho naught plus rho naught alpha delta t, then minus rho naught by rho naught is equal to alpha delta t, and then rho minus rho naught by rho naught alpha is equal to delta t. I don't know what is this. This looks like a relative lowering of uh, electrical resistivity. What do you guys say? Is it? I mean, technically, yeah, it should be because initial resistivity is supposed to be lower. We are considering it as low, and the new resistivity would be higher because let's say we're increasing the temperature in conductors. That's why. So that's one thing we can talk about it. So yeah, but I don't know because this will have some limitations, right? This law should have some limitations. If we have negative delta t, then what is this? It will be negative. Then we have 1. So this will be negative, this will be negative, and then cut out. Okay, so that's also positive. Okay, then. And that's fine. Alpha will be the temperature coefficient. I believe that is a constant. Okay, it's given here. I'll check that out. I'll check that out. Okay, we have to practice this again for this one. Even though it's not a derivation, it's just like having some type of equation formation. And then we have some graphs. So till ohmic and non-ohmic devices, we'll revise everything we have learned, and again like in a faster way, and that's what we are going to do again and again, so that we don't forget anything about that what we are learning overall. So that we can keep everything in our mind all at once. Then we have current density. We'll skip some derivations. We'll just know the formula for now. Then conductance and conductivity, and then superconductivity. This one, internal resistance, EMF, and TPD. This will take some time, I guess. um, we'll skip derivations again, but yes, till internal resistance, EMF, and TPD. Then Wheatstone bridge. Okay, so Wheatstone bridge, internal resistance, EMF, TPD, and Kirchhoff's law. These three. These are the ones which will be left out if we complete it till superconductivity. So we have to aim to complete superconductivity first. Then there will be only three concepts left for the theory part, and that's where we'll complete the theory part of this unit. Then we'll move on to the derivations and complete those derivations too. That's how we're going to do. Derivations are not there as much as I thought, but okay, it's fine. Some derivations are easy, so we can complete them as fast as possible when we look at them. And then once those derivations are over, we'll practice those numericals. We'll have to practice every numericals actually, so that we don't cause or create any confusion. Once that's done, once the numericals are done, what we will be doing is we'll try actually practicing, or we'll actually try to do the other chapters, because current electricity is something that I've not reached or I learned in the batch. So I'm gonna actually not study much about it. Once I complete it, I just completed it. That's one thing I will know about it. So till there, yes, this much. Once I complete current electricity, I complete current electricity. That's one such thought I'm gonna keep on my mind. Then once that's done, I'm gonna do what is that called? Yeah, I'm gonna be doing this electrostatics from the first chapter, electric charges and fields. From there we'll start it. I have some advantage on the second chapter of the electrostatics, but then first chapter is something which we need to also go through. So yeah, I have studied some parts of each chapter now. Like that's what I can say for sure. But then I'm still not that strong. I have to make it stronger. That's one thing. So electrostatics, we have to study those in J level, not full chapter because we didn't complete the second chapter yet for J. Then or NEET level, you can say NEET level too. And then what else? Then we have to practice a paper because physics is something which we have to be totally ready of. Yeah. 1 minute. I'll go drink and water and come back. I'll also pray. Man, oh god. Oh, the image is twisted. I should use my phone then. Bro. Oh, there's some questions actually. Wait, how can I zoom? Okay, electrical energy and power was also there. Joule's law of heating effect. Oh, Kirchhoff's law. Okay. All right. Oops. Okay, so let's move on. Where was I? Hey there, bro. I see when we were watching me. I mean, I have YouTube live control panel, so based on that, I can actually check who's watching me right now. So yeah. for nickel or for copper, for nickel, for copper, and for what? My beer formation is very weird actually. For nickel, for copper, and for silicon. Semiconductors, right? So silicon. Semiconductor. Okay, yeah, so let me just go through this so quickly so that we can understand. What we have learned about this is that rho is equal to rho naught 1 minus alpha delta t. Still do this for r naught 1 minus alpha delta t. That doesn't make changes to. However, if you want to try this out, this is rho minus rho naught by alpha, which is equal to delta t, and we can also write this as r minus r naught by r naught delta t is equal to alpha. Alpha is temperature coefficient. This is nothing, this is just a box. Coefficient. Alpha greater than 0 for metals, from conductors. Uh, Alpha lesser than 0 for wait, what was it? Semiconductors, as there is a different case, and for alloys it is very very small. Alloys. So that's one thing. Or okay, so for semiconductors, temperature increased and number of density increased, and rho is decreased. Case of relaxation time does not is not significant here. But for the conductors, the temperature is increased, the vibration is increased, collisions are increased, relaxation time is decreased, and resistivity is increased. So in this case, yeah, number density is not significant here because it only depends on the nature of the conductor or formation. Yeah, and it is number density is also the collective of or number of free electrons to carry the current, right? So current depends on that factor too. So, but that is for rho inversely proportional to 1 by n. That's one thing too. For alloys, increasing or decreasing the temperature does not affect the resistivity or resistance, or will have a small change, very small change in resistivity or resistance. That's one thing. That's why manganese and constantins are used in making standard wires for resistors. Then rho is inversely proportional to n because number density is basically forming or giving us the um, how many breadsticks are there? Okay, there are pretty much a lot. I did not see that coming. Oops. Okay. Well, that's weird. I was just checking this. Alright. Current depends on collective movements of free electrons. Then number density is inverse. I saw when we were watching me. I don't know who was it. But hey there, bro. Hi. Resistivity is inversely proportional to 1 by n. Because n depends on the nature of the material of conductor, and resistivity also does depend on this. So it's another reason for resistivity being inversely proportional to 1 by n. Okay, and e squared, sorry, m by n e squared tau. Alright, to talk about the graphs, let me practice it again. This is for alloys. This is for the conductor. This is for the semiconductor. Wait. Alright. That's pretty weird actually. What do you guys say about breadsticks? Look at this. What happened? Okay, let me just take one bite without putting it into Nutella. Tastes like a normal biscuit, which does not have a lot of taste into it. That's what I can say. Anyways, let's move on. Next is ohmic and non-ohmic devices. Okay, wait. That's not the one thing I want. Follows an exponential curve. Yes, it's like a cubic one. You know the cubic ones. Hmm. Okay. You know what's weird actually? Like some people make these types of laws, and then they get so confused when they find out that there are some materials which do not follow this at all. Like how difficult is it to like do this? This is so difficult. In fact, super difficult. Super difficult. Super duper difficult. Oh my god, bro. I don't want to make it fall, but look at that. I wanna take it. Yep, that's it. I'm gonna throw this. Whew, I was taking the whole Nutella dip. I know you may feel like I'm getting distracted. I mean, yeah, kind of, but I was just eating this. I like this. It's good. Oops, oops. Yes, let's go. Let's continue. We are at the topic of current density now. So ohmic devices are those devices which would obey the Ohm's law and have their graph of VI as linear. But for this, the non-ohmic devices, they will have their graphs as non-linear, which means that they will have an exponential graph, and they would not also obey the Ohm's law. So basically, if we give an example for this, it is a diode. Diodes are the examples. Like you will have one current type which is in milliamperes in positive y-axis, and another current type in microamperes in the negative y-axis, then voltage on the x-axis, where we would show the exponential graph. There are two types of currents that I could actually like see in this as for the characteristic curve of diode. So that's one thing. So this is the characteristic curve of diode. Characteristic curve of diode. You're gonna do that. Now current density. The amount of electric current flowing per unit area of the conductor helps perpendicular to the flow of charge. Okay, so current density, it is represented by the letter capital J. I think the last time the only unit physical quantity that was represented by capital J was impulse in 11th. Now it's current density. J is equal to I by A. J is treated as vector quantity because current is also no, my bad. Current is not. Current is not a vector quantity. I'm sorry. You know what's weird about current density? Even though it looks like a scalar quantity, it is a vector quantity. It is treated as vector quantity. It is pretty weird. If you look at the formula of current density, it is actually an EVD, which kind of makes sense because maybe it is following the direction of the drift velocity. So maybe that's true too. But that is so weird. Like current density is a vector quantity. What? Then we have conductance and conductivity. There's a derivation based on this. We'll skip that derivation and then we'll just write the formulas right now. Then we'll write the superconductivity topic. I'm gonna mute myself right now and then I'll unmute it back again. 1 minute, just for a while, okay? Let's go. Yo, let's go, man. We're almost gonna complete this. We have superconductivity topic left. Okay, so the graphs are simple actually in this topic. They're not that concept. Hey Robert W, how are you doing, man? How are you? कैसे हो भाई? How are you, man? Hope you're doing well. Are you preparing for accountancy, like for accounts exam? إن الخزي اليوم والسوء على الكافرين الذين تتوفى. You're welcome. You're welcome.
Yeah, I was wearing my headphones. So how's accountancy right now for 12th standard? For me, physics is okay, it's great. It's actually looking fine. It's not hard actually. But maybe the questions from the exam may be difficult. That's one thing for physics. What about accountancy? Yeah, my sister is attending Quran class. That's why I'm using headphones to like speak slowly. Or else it will disturb her and the class. How are you doing? I think you're doing great. That's what you have said. Yes. Thanks, yaar. Same to you, bro. Yes. So you're preparing for accounts. I'm preparing for physics, second unit, current electricity. If you don't know. Also, when are you gonna like? Are you planning any future streams? Uh, what time? Like 12 o'clock, 1 o'clock? At what time will you be staying up late night? Like at midnight? What time? Same here also. I'll be practicing a lot of physics problems today and we'll be dealing with a lot of things. We have technically 2 units or 3 chapters for exam. 1 unit electrostatics, which is consisting of electric for charges and fields. Then yeah, electric potential and capacitance. Then we have the current electricity chapter, which is another unit. Probably 12 to 1. Okay. Because I gotta cover it up and practice questions. I got it. I got it. So 12 to 1 a.m. Okay, then. All the best for that, you know. All the best. Also, are you planning any future live streams? Like, are you planning any? If not, it's fine. No problem. No force. Accountancy. I see. Okay. We also have 3 chapters, but we call it as units. 2 units, basically. 1 unit contains 2 chapters. The other unit also contains only 1 chapter. Uh, After exams, inshallah. Okay, no problem. Depends on you, man. I'm not gonna force you at all. No, inshallah. Okay, after exams you'll stream. That's great to know, by the way. But inshallah, it depends fully on you. No force at all. How was today's exam for you? Like business studies. How was business studies exam? I think it went great for you. It was fine, I guess. Oh, it's no problem, man. No problem. Even though if it is going bad, it no problem. I hope that you get good marks. I prayed for everyone. And yes, believe in yourself. So yes, all the best to Robert W. You can do this. Anyways, I got a dip. See y'all. Lol. Okay, yeah. Okay, bro. Have fun. Allah Hafiz. Bye. Yes, Allah Hafiz. I have to also cover my physics portion. I'm gonna remove my headphones.
Bye. Bye, bro. EMF, TPD, and internal resistance of the cell. So, EMF. The max potential difference between the terminals of a cell when no current is drawn from the cell is known as EMF. TPD is the of a cell is the potential difference between the terminal and between its terminals and a closed circuit when current is drawn from the cell. Generally, EMF is greater than TPD, but when cell is charged with electrical source, then we will say that TPD of a cell is greater than EMF of cell. For a cell. This concept is a bit tough for me, I guess, maybe, but I feel like you can cover this too. The rest all concepts that we studied were easy. Okay, so diode curve, then exponential curve will be there. This is MA, this is mu A, this is volts. Anyways, I gotta dip seal on. I like his way of saying it. That's a good style of, that's very casual. By Allah Hafiz. Allah Hafiz. Uh, then we have internal resistance. It is the opposition offered by the electrolytes and electrodes of a cell. I don't know why, but current electricity and electrochemistry are so related, bro. Like there are some concepts which are really similar to that of the both chapters that I've studied. Like no, I mean I have studied electrochemistry, but now I'm studying current electricity, right? So when I'm going through across this, I can see and feel that same topic that I've studied. Like look at this. It is opposition of okay. I have not studied about this, but it's very similar. Like EMF. EMF is literally the same thing that we studied about this, like E naught cell, E cell. Those ones. Then, not only that, we studied one another topic, conductance and conductivity. We also studied that in electrochemistry. Like that is interesting. Yeah, superconductivity too. Superconductivity. Like actually, we studied about superconductors. We didn't study about superconductivity. But yes, it is really related if you ask me about this. So superconductivity is a property of the material, like a metal or an alloy, where it is exhibited by this material at a very low temperature. The temperature at which the material shows superconductivity is known as transition temperature or critical temperature, where the magnetic field is also expelled out. Then expelled. That's what I can say. A magnetic field is expelled is another point which I didn't see in the notes or any in the textbook. I guess maybe I didn't even see the textbook. I have to check because usually many people don't bother with the physics textbook. And then what else? What else can we ask? Yeah, let's say example Hg at 4.2 Kelvin, where it will show superconductivity. Resistivity varying with temperature. So it's something like this, where resistivity varies with temperature. So at a point when it comes here, the uses of this is that they are used in making of electromagnets and used in high-speed computers. Strong electromagnets, my bad. Strong electromagnets. I did not mention that. All right. I have to pray another prayer. Oh God, it's very late. I have to go pray now. And then I'll continue. So we have done with this. Once I come back, we'll revise this again, like the whole theory part. This should take under like 5 to 10 minutes, and then we'll start off with EMF, TPD, and internal resistance of a cell, then Kirchhoff's law and Wheatstone bridge, and then the whole theory part is finished. Then we'll move on to derivations part. Derivations part will take at least like 2 to 3 hours. We have to focus on each derivation very carefully and nicely, such that we remember and retain them for a long time. And talking about formulas, we have covered a lot of formulas like I is equal to NaEVD. You know what? Let's just tell. I'll talk about it later. We can revise it later, right? That's why. So yes. Not tough. Huh? Not tough. I'm back. Sorry, I left. I just wanted to pray. Finally. Let's revise now. I'm gonna do fast revision. Charges in motion, exhibit EF and MF. Rate of flow of electric charge through area of cross section of the conductor in a definite direction. Current I by is equal to Q by A. Then we have this, which is in amperes. Positively charged flow is known as conventional. To that opposite is electron current. Then the both are opposite in direction. Conductors have free electrons. This is a revision. I'm just doing revision by myself. If you don't know. Conductors have free electrons. They move randomly. They have a random motion basically with, or there was a name for this. I don't remember the name. Okay, we studied this in kinetic theory of gases last year. Like I don't remember it. Is it Brownian motion? I'm not sure. Was it? What do you call it? Random motion. What do you call a random motion? Motion of particles. Let's say particles. Is it Brownian motion? Brownian motion. Okay, never mind. Yes, remember it. Brownian motion. Let's go. I was correct. Here, I thought I was going wrong. Okay, never mind. Anyways, the thermal velocity varies from 10 raised to 5 to 10 raised to 6 for electrons, and the due to Brownian motion or the random motion, their average thermal velocity is 0. EF is applied across this in a definite direction where the electrons will move opposite to that, opposite to that of the EF direction, which means that the overall thing is that it gets drifted into the direction it's moving on. Basically, the electrons will do that, and then the velocity of that drifting, where the electrons will move into that direction, is known as uh, drift velocity. For the drift velocity, um, v is equal to E capital E tau by m. That's one thing. Acceleration is very short-lived and takes place successively at each collision, and then or tau is the relaxation time at the time interval between two successive collisions. Mobility, the ratio of drift velocity, and what can you say? The ratio of drift velocity and the electric field applied across it, and which are basically tau by m. Center mu. Relation between drift velocity and electric current is equal to NAEVD. The current flowing through the conductor is directly proportional to the potential difference across the ends of the conductor, provided the temperature and physical conditions remains unchanged. V is equal to IR, the nature of material, temperature, and dimensions. Slope R is a straight line. Then here study this, and this. The resistance of a conductor is directly proportional to length and inversely proportional to A. R directly proportional to L, inversely proportional to A. So R is equal to ml by Na squared tau. R is equal to ml by Ne squared tau. That is basically rho is equal to m by Ne squared tau. R is equal to ml by A Ne squared tau. Or NE square A tau, or NA square tau. Oh my god. ml by NA square tau is equal to resistance. Rho depends upon the material of conductor but does not depend upon the what do you call it, dimensions. And then it is also dependent upon the relaxation time, and also dependent upon the number density of electrons, or free electrons, and it is also dependent upon temperature, if it has a relation in based on the material of the based on the material nature of material. um, if it is a conductor, no, let's talk about temperature later. Let's say that resistivity is inversely proportional to uh, tau, because the relaxation, as the temperature increases, the vibration increases, collisions increases, and collision increasing means less time for after each successive collision, and that will cause less decrease in relaxation time, and that will increase the resistivity. So resistivity is basically kind of increasing along with the temperature. And talking about number density of electrons, it is inversely proportional to resistivity. The reason why it is inversely proportional, because the number density of electrons are basically depending on the material of the nature of the material, not conductor actually, and not like nature of the material. It could be alloys, right? It could be semiconductors and all that stuff. Basically, and n is basically talking about mainly with semiconductors here, because it is significant there. And then the reason why we take the number density of electrons inversely proportional to resistivity, because the collectively free electrons are the ones that determine the amount of current, right? That's why. So this is very important too. Then we have the variation of we also studied about one such topic, a variation of electrical resistivity temperature, where for conductors the temperature will increase if it is vibration increases, collision increases, the relaxation time decreases, and resistivity increases. Number density is not significant here. It is not useful in this one. For variation of electrical resistivity, even though number density increases actually in conductors if the temperature is increased, but it is not considered. And then for the semiconductors, the relaxation time would decrease when we are increasing the temperature is increased, number density is also increased, so rho is decreased. Here tau is or the um, relaxation time is decreased in this case. Sorry, which means that it is not significant, by the way, but it's not significant in semiconductors. For alloys, increasing or decreasing the temperature uh, would not affect the uh, resistance or resistivity, or may have a negligible change. And that's why manganese, constantan, and nichrome wires are the ones that are made as a standard wire for resistors. Dependence of electrical resistivity, where rho is equal to rho naught into 1 plus alpha delta t. If we calculate it, it will be rho minus rho naught by rho naught alpha is equal to delta t, or r minus r naught by r naught delta t is equal to alpha, where alpha is temperature coefficient, where and delta t is temperature difference. And then what else? If alpha is positive, then it shows that for metals alpha will be positive, for semiconductors alpha is negative, and uh, semi uh, for alloys alpha is very very small. And then it is unaffected by temperature. It's a small thing. Then resistivity time graph resistivity temperature graph for alloys will be slight increase. Resistivity with the temperature for metals will be a increasing curve. And then resistivity with increase in 1 minute. We'll call it here. Resistivity with temperature will have a decrease in it, because or inversely proportional, because the material that we'll be using here will be semiconductors. Then talking about ohmic and non-ohmic devices. Ohmic devices obeys Ohm's law, and non-ohmic devices would not obey the Ohm's law. In ohmic devices, the relation between the volts or potential difference and current is a linear relation, and then in non-ohmic devices there is no linear relation. And then example of non-ohmic devices is diodes. The curve of diode will be an exponential curve, with the y-axis, positive y-axis being milliampere and negative y-axis being microampere for another current. Then voltage being the x-axis. Then current density, capital J, which is the amount of current passing through a unit area of the conductor, uh, perpendicular to the flow of charge. It is treated as a vector quantity. Its formula is I by A. Did not A is equal to I by A. Yeah, it's Then I is equal to any EVD, so J is equal to N EVD. So if you want to find the formula of J, sorry, VD in terms of J, so it's gonna be N J and EVD, right? So J by NE is equal to VD. Then J is equal to 1 by R. Passport All right, we have revised for 5 to 10 minutes, which means that we have done this. Now we are moving on to all the last three concepts of the theory of this chapter, and then we will do derivations. Okay, so yeah, I know, I've been taking so much time for theory, but I want to master these concepts very well because there is a chance that it can come from anywhere and any place. So we have to be really careful for that. And wait, I'm just joking. We are not gonna give up. EMF, the maximum potential difference developed between, not developed, between the terminals in an open circuit is known as the EMF, where no current is drawn. Yep. Units is joule per coulomb or volt. Yeah, EMF is basically potential actually volts. We also studied this in electrochemistry, but there was another thing. You know what? Actually, I know it's crazy to know, but I just want to know the full form of full form of EMF. Because trust me, bro, like trust me, I had no idea what was the full form of EMF. Trust me. Electromotive force. Oh, then and TPD. TPD. Let's do TPD too. TPD. That's total potential difference, right? Terminal potential difference. Oh, okay. Now I know. Now I know. So EMF, electromotive force. Thank God I got to know this. Finally, bro. Like I had no idea what was this EMF thingy at first. Now I got to know nicely. Like the full form. Then TPD, it is terminal potential difference. And we now have to study about internal resistance of a cell. Internal resistance of a cell. which is something new. Actually, we need to talk about it. Yeah, if anyone wants to video start, it's gonna be. Wait, I wanna know how we draw the video start. That is hard. You know what? Close the keyboard. Yeah. Also about the formulas, which we have learned overall. I is equal to Na EVD. VD is equal to E capital E tau by M. Then R is equal to ML by square. Sorry, NAE square. E square tau, yeah, and E square tau. Then R resistance is equal to rel by A or VI. Rho is equal to M by N E square tau. Then joules, J is equal to I by A. Yeah, okay. So that's J is equal to VD by NE. VD is equal to what else is there? J by N. Okay. Yeah, J is also equal to sigma E. That's one thing. I forgot about that. So conductivity, right? So J is equal to sigma capital E. Then mobility E tau by M. Then R is equal to rho L by A. J is equal to NEVD. So yeah. EMF, TPD, and internal resistance. So EMF, basically, or known as electromotive force, is basically expressed in the units of joule per coulomb or volts, which is basically potential. According to me, both are measured in volts. Yes, they are presenting electric potential. Basically, what we can talk about. Okay, wait. Okay, yeah, they represent the electric potential of a battery or a cell, but they differ based on whether current is. Hmm. Oh yeah, whether current is not flowing or not. Yes, yes. In the case of EMF, the thing about this is that between the terminals of a cell, when no current is drawn, there is maximum potential difference. And then for the TPD or the terminal potential difference, the circuit should be closed for that, between the terminals, where the current should be drawn. And it says that the EMF should be greater than TPD, but the EMF of cell is lesser than TPD of a cell in case if the TPD cell has more is charged with an electric source. Oh, it's charged with an electric source. Okay, cell is charged with an electric source. Okay. Hmm. That's true though, because EMF is like the no current should be drawn for that, so maximum potential difference. That's true. Hmm. Oh yeah, I think here the EMF at TPD measure is done through voltmeter, as far as I know. This is the cell. This is the internal resistance, smaller cell, and then the switch. Okay. 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 Let's do this. Okay. Between the terminals of a cell where no current is drawn. Let me come up. where no current is drawn. Is drawn. And yeah, where no current is drawn. That is one thing. Yeah, unit here is joule per coulomb or volts. Joule per coulomb or volts. Then TPD. They didn't write a full form for this. They are like, yeah, EMF and TPD. Hey, 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 hey. Okay. It is the potential difference between the terminals of the cells where the current is drawn out from the cell. From the cell in a closed circuit. In a closed circuit. Hmm. Okay. Overall, this is also having both the units of these. Yeah, they are also they also have a unit of joule per coulomb or joules. That's true. That's true. 80 volt per meter. Okay. Yeah, that makes sense. What else is there? Yeah. When cell is charged. I write a lot, but still, this is practice. Cell is charged, with an electric source from an electric source. This is not read it, but still. EMF cell will be lesser than generally greater than TPD. TPD. So EMF of the cell, TPD of the cell. Okay. Internal resistance of the cell. Now this is a bit different. This is not the potential difference. This is actually a bit different from the others. Okay, this topic is something pretty much new for me, so I'm gonna go through it again, and then we're gonna go for internal resistance. I have some idea about internal resistance though, but not much about EMF, TPD, and internal resistance. Higher the temperature of an electrolyte, lesser is the internal resistance. You know what I might like? Yeah, that's true. Actually, internal resistance is less for the because the temperature of electrolyte is increased, and we studied this in chemistry too. Like, I mean, I studied this in chemistry. My bad, not we. My bad. Like, so there are some people who have not like learned about this. So my bad. Higher the concentration of electrolyte, higher is the internal resistance. That's also true. It decreases with the passage of time and usage of cell. Nice. Yeah, technically that's true because we studied about this internal resistance. Yeah. Increasing with the passage of time and usage of cell. That is truly logical. Like, that is an experimental fact, basically. Like, we get to know this from the experiments. Like, when you're trying to actually keep a closed circuit, then you find out that after a small amount of, not small, after some certain time, you'll find that the cell becomes really hot. So it's because of that internal resistance. And then we have the derivations, only. Not all the derivations. Wait, there's Wheatstone bridge, which we need to cover, and Kirchhoff's law. And this will take some time. Yeah, I know this will take some time, but we ain't giving up. We will be staying awake for a long time, and then we'll complete the question practice too. So let's complete this. It is the opposition or resistance offered by the electrolyte and electrodes of a cell. Offered by electrolyte and opposition offered by electrolyte and what else? And the position offered by electrolyte and the huh? What? 1 minute. Yeah, and the electrode. I don't know why I'm thinking so much. This it affects. It affects. Okay, it affects. Increases the temperature as time passes by. No, no, with the passage of time, due to passage of time and due to passage of time. Let's say that. I don't want to say the exact statement because it looks like you're actually just mugging up. But yeah, we need to know the points too, right? So yeah, usage of the cell, concentration of electrolytes would show an increase in internal resistance. I don't know why, but I feel like internal resistance should be belonging as a chemistry topic, because we never studied this in chemistry, but this is really related to chemistry. Concentration of electrolyte would show an increase in internal resistance. Then the temperature, increasing the temperature would decrease the electrolyte, would decrease the resistivity, sorry, electrical resistance. Mm. Decreases the internal resistance. Okay. Now for the diagrams, relation between EMF and TUPD. Oh wait, is this a? Oh, this is a derivation, right? No, no. Okay, this is not derivation, is it? This is EMF. Okay. So that is not electric field. That's EMF. Okay, got it. Okay, you know what? Let's just first draw the circuit because it's there technically. So we'll just draw that. It gives us an idea. That's why we'll just draw that. So basically, there is EMF which is basically a voltmeter attached to it. Then we got the cell here with its internal resistance R, small r, okay, and then we got the yeah, and then we have the small cell. What do you call it? Open, and then we have the resistance. I hope they don't tell us to draw these diagrams, man. That would be crazy. I mean, even though it's mentioned here, I'm just practicing it just in case, but still, that would be worse. Yeah, you know what? I'll just study this. Internal resistance smaller. We'll label this. This is closed. Then resistance. Yeah. So technically, this is like small r, small r, capital R, capital R. This is TPD. That is EMF. That is closed. That is open. What else do I need to say? Not gonna lie, that looks like a capacitor. That cell representation. Let me just elongate that positive terminal. The way I like drew the cell for the EMF looks like a capacitor. So I just extended the positive terminal, so it doesn't look like that. Alright, so looks like we have done this topic too. We'll just go through this again. EMF, it is the max potential difference between the terminals of a cell where current is not drawn out um, from the cell, and this basically has the unit of joule per coulomb or volts, which is expressed in volts. And then we have TPD, terminal potential difference. EMF is electromotive force, and TPD is to terminal potential difference. TPD basically is like the potential difference between the terminals of this cell, where the current will be drawn out from the cell in a closed circuit. And TPD, it generally EMF is greater than TPD, but if you talk about the cell when it is charged by an electric source, then we'll say that yeah, the TPD of a cell is greater than EMF of the cell. So yeah, I think that's it. We have Wheatstone Bridge, Wheatstone Bridge, Wheatstone Bridge. What else do we have? Wheatstone. Let's write that down. Wheatstone's Bridge. Now first I will draw the diagram because I feel like the diagram is much easier for me to draw. Maybe. What do you guys say? Okay, let me draw the diagram properly for this one. So let's say that I have a middle. This is a galvanometer, and this one here. For those who don't know what galvanometer is, it is basically an ammeter but expresses currents in very small values like milliamperes. Whereas ammeters will be expressing them in amperes, like large amounts, because the current expressed in amperes are already very large. So we express them in milliamperes, microamperes, and all that stuff. That same goes for charge too. Not millicoulombs, microcoulombs, microcoulomb. Millicoulomb is very weird. Then some people also express it in nanocoulombs. You know, so that's one thing. I mean, not some people, it's some questions. My bad. Uh, anyways, we'll do this. We'll draw the resistance of each. Okay. Let's say that cell here is positive, negative terminal. I think there is a chance they might ask us to draw this. Who knows? Oh, yeah, the diagram labeling is crazy about this one though. Need to learn Kirchhoff's law for this, which we're gonna do. Okay. Oh yeah, let me also write down here A, B, C, D. This is I1. This is I minus I1. This is I1 minus IG. This is I minus I1 plus IG. Okay, so basically what happened here is this is first of all current. Okay, we're gonna put I here. Then we are gonna say that this is I1. This is I minus I1, and then here we have another one which is moving downwards. I believe that is known as IG. So here it will be I minus I1 minus IG, or no, I1. Oh, okay, okay, it's I1. Okay, I1 minus IG. Okay, yeah, you have to be careful here. Uh, this will be I minus I1 plus IG. Yeah, that's correct. Okay, I believe that we have done it correctly. Yes, we did it. Now we have to like study the theory part of this. I can show it to you actually. It looks something like this. Um, I think that there is too much brightness. 1 minute. Yeah. This is the EMF. This is the TPD. You can see that there is like an open circuit here. This one is a closed one, and then we got the Wheatstone bridge. It's here. This one. This is the Wheatstone bridge. Can I like get it closer? This is the Wheatstone bridge I was talking about. It's a good. It's a kind of a good type of circuit. And what I do know about this is that this is a bit important topic. Like we need to have an idea about this topic. Then meter bridge, practical form of Wheatstone bridge is known as a meter bridge. Basically, we will study that in practicals, physics practicals. I don't I thought about that. I like this experiment actually, even though we have not done it yet. But I feel like this experiment is gonna be fun, for sure. Then like what I'm gonna do, I before after exams I'm just gonna like focus on physics practicals because physics practicals are the upcoming ones, and we will also focus on batch 2 because after exams we have to do a lot of batch work. That's one thing. um, IG is equal to 0. Okay, so let me draw this. Let me first read it. When key is closed, the galvanometer shows presence of current through it. The value of resistance R is adjusted in such a way that the galvanometer shows no deflection. At this stage, the potential at the points B and D is equal. Yes, that's true. And what else? It's equal, and no current flows through the galvanometer, which means the potential difference at for B and D will be 0, and no current flows through this galvanometer at this stage for at B and D, right? So yeah, then and no current flows through the galvanometer at this stage. The bridge is balanced. Then P by Q is equal to R by S. So in a Wheatstone bridge, some amount of electric current will pass through the galvanometer where the galvanometer, where the galvanometer show the deflection. Oh yeah, we'll also name these. Let's say this is P, Q, R, S. Let's go. Uh, where the galvanometer would be. In a Wheatstone bridge, some amount of electric current would pass through the galvanometer, where the galvanometer would oh, show deflection. Okay. The any one of the resistance can be adjusted in such a way that can be adjusted in such a way that the wait, not this one, that the and some amount of electric current would pass through the galvanometer, where the galvanometer would show deflection. Any one of the resistance can be adjusted in such a way that the that the current that the galvanometer would stop showing deflection, indicating that current doesn't stop flowing through it, and the potentials at B and D became equal. Thus, the Wheatstone bridge would come and Wheatstone bridge would be under the balanced state, and the equation formed, and the equation would be P by Q is equal to R by S. That's what I know. P by Q is equal to R by S. Some people will write it as R1 by R2 is equal to R3 by R4, which is also correct. Uh, like they just changed the name, like R1 by R2 is equal to R3 by R4. That's not wrong too. So it's like R1 is equal to R2 R3 by R4. Not at all wrong. That's correct too. If they want to find any resistance, they can do that. Yeah, we also studied about this in physics practical. So yeah, that's one thing. For now, I'm not gonna do that. What I'm gonna be doing is now we have completed Wheatstone Bridge too. I'll just check the explanation for Wheatstone Bridge, because I want to know if there is any exact statement for it. What is Wheatstone Bridge? Electric circuit for precisely measuring the electric, measuring the unknown resistance. My bad, sorry. Okay, so I think we had done this part too. Let me close this. Alright, so we have done Wheatstone Bridge. This. Pretty much we have completed the whole theory part of this chapter. That is a good thing. Yo, come on, man. Ouch, my leg. Alright, Goat Live. Okay, what is this, bro? Huh? Oh, okay, this wasn't the one. Maybe I need to use phone. Let me bring my phone, and I have to go to toilet. It's a bit urgent again. Man, I know I move a lot of times, but still. Okay, so we have completed the theory part. We also practiced a lot. So yes, once the whole theory part is done, we'll just revise and do derivations. That's it. Then we'll do numericals.
Hi, 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 hi. Hey. Oh wow. No, like actually. Eh, vaya, I think I'm had him, but it's fine. He's chiều thế rồi à. Yeah. Hey, chiều thế hả bà? Eh, chiuro che tu me lo mandi porto te ci prego, stupid. E it was fun, guys. And I was like, gotta go. Dip, see hello.
Bye, Allah Hafiz. After exams, I will. Oh my girl, slap. I I got 3 chapters because I gotta recover Bali 201. Well, that was fun. Not gonna lie.
Let's go. We are. I don't know why is it like this, bro. Come on. Like, yeah, clavicles. Can you see my collarbone? Boom. This is my collarbone. Yeah. So we have to learn this. The heat period. Okay, so we are gonna learn this, and then the theory part is over. Then we're gonna move on to derivations. This helps. Algebraic sum of all voltages, potential difference across all elements, and the heat produced in a conductor depends upon. Okay, so the work done by an electric source to maintain the current in an electrical circuit for like maintaining the steady flow of electric charges is known as. I don't know why my opinion is literally being shown. Like that looks so weird, man. You know, like, bro, why is this so small, bro? Anyways, you know what? Let's just move on. It looks so weird. Like, kind of looks irritating. Kind of makes me uncomfortable whenever I see this or just this. First law, junction law. Okay, the charge is pretty much high. The heat produced in a conductor depends upon square of current flowing through it. H is equal to I square RT or is equal to H is equal to I square RT by 4.2. Okay, let's go. Let's lock in. The heat produced in a conductor is directly proportional. Okay. The heat produced in the conductor depends upon the square of the current, the the square of the current flowing through it, resistance of the conductor, and time for which the conductor uh, time for which the conductor flows through it. No, so for which the current flows through it. Why? I didn't know that Kirchhoff's law contained both the laws, the junction rule and loop rule. So I have to learn both the laws. That's a bit of weird thingy, by the way. So we need to learn Coulomb's law, Gaussian's law, these two laws. I don't know whether there is a law in second chapter. I don't think so. No, no, I'm not sure there's one laws. Yes. But yeah, let's move on. Yeah. So heat produced in a conductor, it depends upon the square of the current flowing through it, the resistance of the conductor, and the time of which of time and time for which the current flows through it. Almost close. H is equal to I square RT, or H is equal to I square RT by 4.2 calories in terms of calories. There is another way to write this thing. I forgot which was the way to do it. Okay, last time. The heat produced in a conductor depends upon the current flowing through it, the square of the current flowing through it, the resistance of the conductor, the time through which the conductor flows, time which the conductor, the time which current flows through it, for which okay the time for which the current flows through, time for which the current flows through. Kirchhoff's law. Algebraic sum of all currents and meeting at a junction into closed electric current is zero. Algebraic sum of all currents meeting at in a junction in a closed meeting at a junction in a closed circuit is zero. And then here algebraic sum of all voltages, potential difference across all elements, and EMF of a closed circuit of all closed electrical circuit is zero. Circuit. Now look onto the circuit. I think it's circuit, electrical circuit. Yeah. Heat produced in a conductor is directly proportional to the square of current flowing through it, the resistance of the conductor, and the time for which the current and the time for which the current flows through it. Square of current flows. Yeah. Kirchhoff's law. The all of the electric no what is it? The algebraic sum of all the electric currents at a junction uh, uh, okay, at a junction in an electrical closed circuit is zero. Okay, that's first law. That is junction law. Then loop rule says that algebraic sum of all voltages, potential difference across all elements, and EMF EMF of all closed electrical circuit is zero. Yeah, it's also. So okay, I got it now. The algebraic sum of all the currents at a junction and in a closed electric circuit is zero. Algebraic sum of all voltages, i.e., potent or known as potential difference across all elements, and the EMF in EMF of all the electrical closed circuit is zero. Of all closed electric circuit. Okay, circuit. I think it's circuit, not circuit. Man, I'm getting confused with that pronunciation. It is zero. So summation of E plus summation of delta V is equal to zero. And here it is summation of E. Summation of I. Wait, why E? Oh, EMF. To this, we come to the end of the theory part of this chapter. We have successfully completed every theory part. I'm happy now. I'm satisfied. Let's move on to derivations now. Finally, bro. Okay, wait. Should I eat first? Because I should. They called me for eating. Then derivations. Um, took me 5 hours, literally 5 hours to complete the theory, dude. Imagine the derivations. How much time will that take? I'm scared. But let's actually like stay awake for a large amount of time today, and then tomorrow we'll sleep a bit faster. But this time, yes, we have to lock in. So we'll do the derivations a bit faster, and then we'll so that we get enough time for numericals, because numericals are really important. That'll help us practice more questions in physics. So that's one thing. So derivations. What am I doing, bro? What am I doing? Yo, algebraic sum of all currents at a junction in an electric closed circuit is zero. Algebraic sum of all voltages, potential difference across all points, yes, across all elements. Okay, across all elements, and EMF of all closed electrical circuit, actually electrical closed circuit is E0. So summation of okay. The heat produced in the conductor depends upon the square of the current flowing through it, the resistance of the conductor, and the time for which current flows through it. That is one thing. Electrical energy and power. That's one. Okay. Wheatstone's bridge. We have looked at that. That is one thing. Precisely used. It is a type of it's type of an electric circuit or circuit where it is measuring precisely the resistance.
Yeah.
Thank you. खुबूस खुबूस भी खाया था परवाने खुबूस इसके बाद खुबूस खाया था परवाने इसके बाद नहीं तो खुबूस डालते मुझे क्या नहीं खा ले तो ये थोड़ा खा को एक खा लो करो
अरे तो क्या भी होता है इसमें आया खुबूस देती हूँ साले में खा दूंगा मैं वो देखकर वो चीज
हाय मैन
और खाना नहीं क्या तेरा हाल हो रहा है चीज अच्छा अम्मी अच्छा
चीज अच्छा
आगे ले लिया
नहीं बस चीज का रिडक्शन लगा बस शुक्र ये बात जाओ ये प्लीज अच्छे बच्चे
दर्द से तड़प लग
वो प्लीज
खाना को
ये बा बैठिए अच्छे बेटी कहते हैं प्लीज जा ओए ये बा बोल रही नहीं जाना है anyways let's move on anyways I gotta dip see a lol okay algebraic sum of all the currents at a junction in a closed electric circuit is 0. Algebraic sum of all voltages potential difference in a and in across all elements and EMF of all closed circuit of all electric closed circuit is 0. So that's one thing. So technically we have completed the theory part, guys. We did great here. So we have great idea of what all things we had done. Is there any graph that we have to go through? No, not now. Okay, so let me eat first, and then we'll move on to derivations. We'll be completing derivations a bit faster now than the theory. Now we have some ideas of what we are gonna do. The first derivation that we'll be doing right now is a relation between current and uh, drift velocity. Yes, that's the one. We'll do this first derivation. We'll first read and check how it is done. Then we'll do it by ourselves. If it is really tough and I cannot understand it well, then I'll do it again. That's the thing. If I understood it well, then I'll just do it one time and then we'll move on. That's it. If you and we'll also kind of go through repetitive steps. We'll also try to revise just like we did in theory, so we can keep it in our mind. We also remember that TPD is the terminal potential difference. It is the potential difference between the terminals of the cell in a closed circuit where the current is drawn from these in a closed electric circuit where the current is drawn from this cell, and for the EMF it's the maximum potential difference between the terminals of the cell in an open electric circuit where no current is drawn from it from the cell, and if generally EMF is greater than TPD, but if you charge the cell, TPD is greater than EMF of the cell. Sorry, TPD of the cell is greater than EMF of the cell. Then what else? Superconductivity, we have done that, yes. So I believe that we had done nice, okay, we had done great. Uh, if we need to revise it again, we can do it, no problem. That's not a big problem here now. We have our strengthened the grip. So we will now confidently move on to the next topic. Uh, right now we have like, let me just check once, okay, like this once, if I had missed anything. Electrical resistivity, yes. The formulas, yes. I is equal to NA VT is equal to small e capital E tau by M, and R is equal to VI R, okay. And then, oh yeah, actually this is wrong. This V is equal to IR, and this is rho is equal to M by NE square tau. Joule is equal to I by A. J is equal to I by A. J is equal to sigma capital E. VD is equal to VD by NE small e, yeah. Then VD is equal to VD by NLE, rho NLE. V by rho NLE. That's one thing. Then mobility E tau by M. Then R is equal to rho by A, and J is equal to NEVD. So one formula that I didn't remember. Oh yeah, this one, H is equal to I square RT. New formula that we've learned. Where T is the time, not temperature. Um, Another thing that I wanted to say about this is, yeah, what was it? VD is equal to V by rho NLE. Okay, Captain Molly. Okay, let's say that I'm confident here, and we can cook. We can cook now. So overall, we had done this. Now we'll eat and complete. Next part we'll be doing the derivations. Man, I'm a bit scared because I don't know how long will this take. But we'll try our best. We're not gonna give up. Okay? You have to sacrifice some time for sleeping too. Today we'll be doing that, but tomorrow we shouldn't be doing it. Even though I'll sleep a bit late, that's one thing for sure. Like, yeah, one thing about that for sure. Let me wash my hands and eat.
Arya!
Thermal conduction. I see. Never mind. Wait a minute. You're not supposed to be there. Yeah, you're not supposed to be there. Yep. Okay. Thank you. Let's move on. Bismillah. I'm not gonna study right now. We'll wait for a while. 5 hours have passed by.
खाना उठा जल्दी
हम्म?
क्यों खाना हो रहा नहीं
खा रहे हो?
तो वो सुना था
क्यों क्या हुआ?
वो सुना था क्या
खा उड़े ना.
होना था क्या कुछ
हो क्यों क्या हुआ?
खाने खाने को देता क्या
कुछ बोल रहा में मैं ले लेता हूँ.
नींद आ रही
सो जाओ.
है
आज जल्दी सो जाओ तुम. दो मैं आज लेट आता हूँ थोड़ा. आज वैसे भी सुबह एग्जाम नहीं है.
नींद आ रही है
ओके ओके. Came back, guys. Finally, let's start off again. I ate my dinner now. Weaver has watched my live stream yet. That is good. Okay, that's fine. That's good. 1 minute. Just wait for a while. I'll switch off the video. Just wait for a while, guys. So, I'm back. Okay. Sorry, I came a bit late. I was just eating my dinner. Let's now focus fully on derivations and numericals. That's it. This time we'll do it a bit in a bit faster way. We're not gonna take much time. All right. And once that's done, we'll be doing our other works. Okay. So right now I do not have any table. It's just my feet and the book. That's it. I do not have any table. Pretty weird if you ask me. Okay. Oh no, this one. This is the previous one. Yeah. Main. What's more? So uh relation between VD and I. We need to now prove or we need to derive the formula I is equal to NaEVD. So that's the formula we need to derive. I is equal to NaEVD. We're gonna derive it now. So first of all, we need, according to this, we'll first go, then we'll see the diagram and then do it by ourselves. Consider a conductor of length L and a uniform cross-sectional area capital A, which means that there is no such variations in the uniform of cross-section. Let V capital V be the potential difference across the ends of conductor, then magnitude of electric field is. Now technically E is equal to V by L because electric field into length is gonna give us voltage or potential difference or potential, let's say. If A is the area of cross section of the conductor, n number of electrons per unit vol per unit volume, and charge BQ. So, okay, this one is a bit confusing. T is equal to L by VD. This is a bit confusing. Okay, what? VD is equal to L by T. That's also true. Okay. Q by T. All right, got it. So technically, Q. My bad. Yeah. Yo, come on. And ALE. Okay, it's funny. Just so for no reason. Q is equal to and capital A small L C. E is equal to V by L. Um, I have a doubt on this one. Wait. You're telling me we'll get this. Alright, I got it. L is the length of the conductor. I got it. AL is volume. Yeah. And N into E. Oh, okay. Per unit volume. Let's see. Number of electrons per unit volume. This is a bit confusing one, but okay, let's try. Consider a conductor and area of cross section A. Consider a conductor of length L and area of cross section A, where the current I would pass through it due to drift velocity Vd, um, due to drift velocity Vd. I don't know how long we'll be staying here, but yeah, we'll stay for a long time. Due to drift velocity Vd, due to drift velocity Vd, where the current I would pass through it due to drift velocity Vd. Okay. So what else do I need to say, bro? ED. Okay. let the number of free electrons per unit volume, number of free electrons per unit volume be number density, Bn, which is number density of electrons. Alright, then start. So basically we know that I is equal to Q by T, and we know that the T is basically L by Vd, okay, and we also know that, yeah, Q by T, Q is equal to N A into L into E. That's one thing that we study about this. Let Q be the charge. Q be the charge. That's one thing I will be mentioning here. Now, technically, oh yeah, how is that E is equal to V by L? Help me out. I'm confused. Okay, wait, we need to draw the diagram too, right? So, I'll draw the diagram. L, the battery, then yeah, charge Q, current I, sorry, current is I, yeah, here. And then V is the potential difference across two terminals of the cell. So that's one thing, which is this. T is equal to N into A into L into E divided by time, which is L in by VD. So this gets cut off. So I is equal to N A E V D. So technically I did the derivation, but then I'm confused what's the use of E is equal to V by L here. Like, why are we even using E is equal to V by L? Let me check. Okay, so I'll derive this once again, just to confirmation. E is equal to E by L, 1. Okay, that's one thing. Where Q is equal to N A L E. Got it. This is number density, that's why. I got it. Is equal to L by VD, and I is equal to basically technically Q by T, right? So N A L E by L by VD. Cut off, cut off. N A E V D. क्या हुआ सर? खाना खा रहा था। मैं क्या कि उठ गया ना, क्या हुआ? I is equal to N A E V D. Technically, what did we do here? We basically, I don't know what's the use of this. Well, why are we using this? Of this. There's no purpose. If A is the area of cross section, number density is basically n is equal to number of electrons by A L into A L. That's what we did into is 1 point minus 1.6 into 10 raised to minus 19 coulomb, where that is Q basically. So Q and number density ALE can represent it as this. That is first, second T. One. LE by L by BD. I is equal to NAEBD. Ohm's law. The current passing through the conductor is directly proportional to the potential difference across the ends of the conductor, uh, provided no temperature provided temperature and physical conditions in the change. That's it. Derivation of Ohm's law. Derivation. Let Vd be the drift velocity of electron through a conductor of length. Yo, Gabe owners, how are you doing? Hi, hi, hi. Bro, why did you delete Robert W's message, man? Come on, man. Why? What are you doing, by the way? I'm doing derivations. I'm practicing derivations. Hi. Are you there, Gabe owners? 1 minute. Let me message him. Um, he's still there in my live stream. Let me check. Oh man, he left. Oh, bro, that was only 1 minute. Come on. Oh, in my stream, bro. I thought you were there in my stream. Yes, I saw that. And sorry that I didn't read your messages. Didn't. Sorry that I yes, and I saw that. And sorry that I didn't read your message. Just thank you and same to you. Same to you. Okay. Um. Wait. Before I do this relation between J sigma and P, I want to do that history row. Is equal to NAEVD, where VD get lead tau by m. Something more about this. Since E is equal to V by L, can be written as tau by ml. Second equation 2 in 1, put 2 in 1, then NAE into EV tau by ml. AE square V tau. नहीं मालूम आज थोड़ा लेट आता हूँ. NAE tau by ml. हाँ करो कर ले. be I by V is equal to NAE squared tau by ml, where V by I is equal to ml by NAE squared tau, and this will be V is equal to ml reciprocal. Reciprocal is done. So it's done, and by NAE squared tau but into I. Since all the physical quantities ml by NAE square constants, they can there they can be represented by a one constant, is resistance. Equal to ml. So therefore V is equal to I R, hence proved. Another thing about this is that R can be we can find out rho, so NE squared tau into L by A, so that is rho, that is M by NE squared tau, and then R is equal to rho L by A. It's also derived from this. Between J, sigma, and rho. These are this is another derivation that we'll be dealing with, and then combination of resistors in series and parallel. Then cells in series and parallel. We are slowly moving on to some other concepts of derivation, and sooner or later we'll complete this too. Today is day 50 though. Yeah, it's day 50. 6 hours has been passed by already. 6 hours have been already passed by. Right. No, beard formation is so weird, bro, I swear. Oh, yeah, weird. Okay, so I is equal to NAEVD, where Vd is equal to E tau by m. Vd is equal to so I is overall n a e square e tau by m, where I by a would give us j, that is current density. So n e square e tau by m is current density. That is this one part. Okay, this one part is done. Then sigma is equal to 1 by rho, because conductivity is inverse of resistivity. So, and then resistivity is m by n e square tau. So m by n e square tau is equal to n e square tau by m. And this sigma is equal to n e square tau by m. Yes, it is. Sigma is equal to n e square tau by m. Yeah. Then J is equal to sigma E. That is another formula being formed. Another thing that I've noticed is that I is by A means J is equal to I by A, so that is NAEVD by A is basically NEVD. Okay, that's one thing. So J, since being NEVD, we can take this and we get the value of J by NE. This is one idea. Another, so we got J is equal to sigma E, J is equal to J by NE is equal to VD. Then we got J is equal to N E square E tau by M. We also know that J is equal to NEVD. So yeah, the thing that I need to do now. VD is equal to I by NAE, where I is equal to V by R, and VD is equal to V by R, so RNAE. Why though? Because I is equal to NAE VD. That's one thing. So VD is equal to V by RNA. Sorry, VD is equal to V by rho L into AE into A, where A would get cancelled. Here, yeah, N is also there. N is there, where VD is equal to V by rho LNE. This is another one. This is another one. So there are a lot of formulas being formed here, and this one single derivation. J is equal to NE squared capital E tau by M. Then J is equal to sigma E capital E. Then another one that was formed was VD is equal to J by NE, and J is equal to V by rho ln E. Sorry, VD is equal to rho V by rho ln E. We'll have to do this again because this is a bit big derivation. Bit big because there are so many formulas that we have to derive all at once, and there are three of them. One, two, three, four. No, sorry. Um, Four to go. Four. I need to derive four of these, and then the next one will be. Next one is an easier derivation, so we can complete that fast. Then the other one will take some time because it's a bit new for me. Then yeah, this will take some time. This will take some time for sure. Then we have one more derivation which we need to go through, and then Wheatstone bridge derivation. That P by Q is equal to R by S. That one is also there. So that will take some time. Ouch. Guys, once the derivations are complete, we can finally do numericals, dude. We can finally do numericals. Once the numericals are also done, we can move on to the next chapter if we get some time. That's one thing. Guys, tell me honestly. I want your opinion. Does my face look worse with beard and mustache, or does it look good without beard and mustache? Like, that's what many people say, that I look really bad with my hair and beard and mustache. Like, really? Ouch. I believe that my beard and mustache um, makes me look good, but that's not the main reason I keep my beard and mustache. I mean, I like keeping my mustache for looks though, but yeah, I keep beard for religious purposes. So yeah, one thing about that. But I don't like people saying me to cut it, and I have to do it for sure. I have to do it because just because they say do it. I really don't like that at all. I hate it. Anyways, let's just do it. You know what? Let's start off with the main classic formula. A is equal to mu Vd, where Vd is equal to E W tau by M, where this I is equal to N square E tau by M, and I plus J is equal to N E square E tau by M. That's there. Thus we found the first formula. Yeah. Then we after did that. After completing this, do we need to do the second chapter? What do you guys say? Because second chapter or first chapter? Like, what is your opinion about this? I think we'll do second chapter because I have completed and studied that one chapter once, so it will give me a booster. Not this one. Yeah, my bad. My leg is paining, guys. Sorry. Oh yeah. J sigma is equal to 1 by rho, which is 1 by m by ne square e. That is ne square e by m, and that is the one thing. So sigma is equal to ne square e by m, where we talk about this and that and blah 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 blah. Yeah, blah 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 blah. You know what I mean? You know what I mean, right? Yeah, ne square e by m. What else? What else do I need to say here? Ouch, ouch. sigma is equal to ne square e by m. Yeah, so that is J is equal to sigma e. That's another formula derived. J is equal to ne Vd. So wait, J by ne is equal to Vd. That is another formula derived. One more thing about this is that we know that I is equal to na EVD. So yeah, just one more thing about this. I is equal to na EVD. So what happened is I by a. That's why I choose to show this. So yeah, and AEVD. Then this time I'm gonna take an AE and put it back down. Out is equal to VD, where I is I by an AE, right? So that is equal to VD. So what can we do here? So we can convert I is equal to V by R through Ohm's law. Ohm's law. This we get VD is equal to V by R and AE, which is basically V into A by rho L into N into A into E. So this gets cut off with AA. So we get V by rho L and E. So VD is equal to V by rho L and E. That's another formula. Let's move on to another one. Combination of resistors in series and parallel. Okay. Now this is not that important of a derivation, so let's do this fast and we'll do it once. We'll just look at it and just do it once. This is because it's also easy. That's why. I feel like the relation between J. I think we need to like make a whole formula sheet for this chapter because there are so many formulas that we don't know. Like it's fine if we don't make for electrostatic, sorry, potential and capacitance, but still electric potential and capacitance, it's fine if we don't even put that one up. Ouch. Combination of resistors in series and parallel, that is basically gonna be our work. Let's go. Right? Combination of resistors, let's go, man. Let's start with series. Here the potential difference will vary, that's one thing. So yeah, let this be R1, R2, R3, and V's total potential difference is equal to 1 plus V1 plus V2 plus V3. So when we try to do this, so R, say wait, so IR is equal to IR1 plus IR2 plus IR3. So R is equal to R1 plus R2 by R3. That is done. For series, and this one is a parallel. So Then we have, yeah, we have this time R1, R2, R3 with potential difference V. This time current divides, so I is equal to I1 plus I2 plus I3. And potential difference is constant in this parallel combination. So what will happen is, um, V is equal to IR by Ohm's law, Ohm's law. I is equal to V by R, Ohm's law. Algebraic sum of all currents at a junction in a closed electric circuit is zero, and algebraic sum of all of all voltages, potential difference across all elements, and the EMF of all closed circuit is zero. Okay, you do know Kirchhoff's law now. That is great. Then the heat produced in a conductor depends upon the square of the current flowing through it, resistance of the conductor, time for which current flows through it. Yeah, you know Joule's law of heating effect too now. So that's a pretty new concept. That's why I revised it. So V by R1 plus is equal to V by R2. R1 plus V by R2 plus V by R3. Therefore, 1 by R is equal to 1 by R1 2 plus 1 by R3. So that one is done. We have completed this part too. Another time. This is the what do you call it? Internal resistance of a cell R. This one here, let's say this is EMF. So this one will be basically having a switch open. So that's one thing. So idea we can get, this is R, this is EMF. So open. This one where it is this uh, internal resistance small r, with this being TPD. It's capital R. So that's one such idea. Circuit is closed. Okay, circuit is closed. Let's say that circuit is closed. I is equal to E by R plus R. Now this E here represents EMF, which acts as volt potential, acts as voltage. Okay, that's one thing. So E is equal to I into R plus R. This one will be for EMF case. Then E is equal to IR plus I small r, and that is E is equal to V plus I small r. And here we take this, we get whoa. Yeah. So V is equal to E minus I. Right? I see. Basically, these are not derivations, these are just like conceptual ideas of what you need to know. But okay, okay, this will help. And okay, I need to practice this and understand this. Overall, we are doing great because we are gonna soon complete derivations so fast. That's crazy. Then we'll do numericals. The numericals will be the part where it kind of terrifies me, you know? So we have to be really careful with the numericals. Another thing about this is that this is a formula based chapter, so you have to like we have to like learn the formulas very well for this one. And I feel like we have to be really careful with the electric potential and capacitance. Static potential and capacitance. Electrostatic potential and capacitance is next. Electric charges and fields is easy, so it's not that hard, but yeah, you have to be really careful with this one. Gaussian's law or the electric flux. This is gonna be the tough part for me. This is the tough part. Like it will take some time for me to like understand and learn all these. So yeah. Okay, so when the circuit is closed, I is equal to E by R plus R, where I is into R plus R is equal to E, where this E is EMF. So IR plus I small r is equal to E. This IR is equal to E minus I small r. This IR represents V, so E minus I small r is the way where you can understand this. So yeah. So one basic idea I need to know about this is that whenever I need to derive something, I will based on the basis of this EMF and TPD, we'll have to check this out along with the internal resistance. Then we need to know this formula. Okay, so now let's try to determine this again. I is equal to E by R plus R, where I is equal to R plus R is equal to E, where IR plus I small r is equal to E. This is V is equal to E minus I capital I small r, and this is the overall formula. I'm pretty confident that we will complete full physics till tomorrow, like complete full physics portion. But I have a bit doubt whether I can like complete the J part or NEAT part. I want to do that, and I want to cover that too. If I can do that, then it will be really sufficient for me. Like it will help me a lot. And electric flux is the tough topic for me, if I'm being honest. Out of all the topics that I've studied, electric flux is the toughest one. So every topic has its own way of trolling me. But looks like I can do it. So you know what? Once I complete each and every part of it, the each every type of chapter, learning, then we'll deal with electric flux. Electric flux, you're next. But tomorrow, not now. But yeah, we'll start off with electrostatic potential and capacitance. Once that's done. All right. What's this? What's this white patch? What's that white patch on my nose? What? I don't know what's that white patch. Like what? What? How is that even possible, bro? How is that even possible? Never mind. Determine. 1 minute. I think we have this. Let's check the WhatsApp. What does it say? Um, need a phone for that. 1 minute. doing it. Yo. Okay, so cells in series and parallel, and for identical, and then technically have this. Yes. After that, let me just check. Okay, technically we have this formula. Alright. So we need to write electrical energy and power. Then we need to write the. Oh, there is a derivation based on this. So power derivation, not a big problem because we're gonna complete it in almost like after this. Thank God there are no many statements. Check that later out. I'll check that out later. Alright, we're doing great. This one is done. Let's do the identical solution series. Three cases here are easy. The last one is a bit lengthy. Identical cells in parallel. Okay, here now, E remains same in parallel combination. R effective is equal to 1 by R 1 plus, sorry, 1 by R plus 1 by R goes to 1 by R to give us N by R. This 1 by R effective, specifically N by R. So R effective is equal to R by N. R effective should be R by N plus R, which is R plus N R by N, and taking this we get E by how is this written in R plus N R by N, which is N E by R plus N R. That's R net. The diagram is also withdrawn. It's like this. Hello, bro. This will be E E E R R R. Now here we go. Finally. Okay, is there any diagram for this? Oh, yeah, we did identical. What about this one? Okay, it's something like this. Yeah. And I don't know what all things I missed in this notes. Okay. Well, this one and last different cells in parallel. This one is a bit tough. I'll understand through this one. Technically, two. This is engine. Yeah, finally. Oh my god. I don't know why I was feeling so itchy here. Let's go. Okay, so I got some ideas. So it could be like, E1 minus I1 R1 and is equal to E2 minus I2 R2, where we can actually like write this down as um, V minus E1 by E1 minus V by R1 is equal to I1. This one is E1 E2 minus V by R2 is equal to I2, where I can be divided into I1 plus I2. So I will be basically E1 minus V by R1 plus E2 minus V by R2. So taking this out, think about this is that E1, I have a doubt here, like why is this thing different? Potentials, oh, oh yeah, potential may be different, that's why. I see. C2 R2 by R2 is V by R1 plus. Alright, so we got this one. Same, yeah. V1 by V by R1, where I equivalent will be also be written as E equivalent minus B by R equivalent, which is second equation. What? So what's the difference here? As you can see, we separated this. What are we actually finding though? We should be finding the voltage here, the current. These derivations are lengthy, but they are easy. That's what I can say. Only one derivation is a bit tough, as far as I've seen from here. R equivalent. So you're telling me that I can write this as, or wait, not, let's not say that this is the one. Equivalent by R equivalent minus V by R equivalent. This is second. Comparing 1 and 2. 1 and 2. Where E equivalent by R equivalent. So this is E1 by R1 plus E2 by R2. Okay. So it's like E1 R2 plus E2 R1 by R1 R2. I got this one. Okay. Now we take E equivalent E1 R1 R2. Still didn't get it what we're doing. So we have to check. E1 R2 plus E2 R1 by R1 R2 into R equivalent. So this E equivalent, second equation, right? Yeah, second equation. Okay, wait, V by R equivalent. Alright, so we are moving into some place. Alright. Why am I putting this as second equation though? That's not the one. This is the other one, V by R equivalent, which is V by R1 plus V by R2, which is technically V into 1 by R1 plus 1 by R2. Choose down. Okay, so that is by R, okay, equal V by R equivalent is equal to V by R2 plus R1 by R1 R2. Alright. Say that V is cancelled. Yes, we did that. Now 1 by R equivalent is equal to R2 plus R1 by R1 R2. So basically, if I check this out, I get to know that E equivalent that we solved is equal to E1 R2 plus E2 R1 by R1 R2 into this one will become now R2 plus R1 by, oh shoot, I think I made a mistake. Oh, okay, never mind. So R equivalent is basically equal to R1 R2 by R1 plus R2. Okay, now it's fine. I got scared here. R1 R2 by R1 plus R2, and that should give me E equivalent is equal to, this one should get cut off. So E1 R2 plus E2 R1 by R1 plus R2. Okay, my god, bro, this was so lengthy. That was so lengthy. Okay, I have to go through this derivation once again. So basically, what I got to know from here is, okay, so basically in the first cell, we're taking it as V is equal to E1 minus I1 R1, and V is equal to E2 minus I2 R2. and then we substitute it to get the values of I1 and I2. Then we know that in parallel, voltage is the overall voltage, the total potential difference will be constant, so there's no change in there. But I will be divided so into I1 and I2, so I is equal to I1 plus I2, and here I is equal to E1 minus V by R1 plus E2 minus V by R2, where we will separate them, and then we will write it as E effective. Okay, E1 plus E2, E1 by R1 plus E2 by R2 minus this one. Comparing both the 2 and 1, we get to know that E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2. Then we get this. Then E equivalent is this, and then we get this value. But after that, V by R equivalent is equal to V by 1 by R1 plus 1 by R2, and then we get this R2 plus R1 by R1 R2. We get this as R equivalent. Then overall, with this, we should be getting V by R equivalent is equal to V into 1 by R1 plus V plus 1 by R2. That is 1 by R equivalent is equal to R2 plus R1 by R1 R2. Then V by R equivalent. Alright, 1 by R equivalent is equal to this. Then this is the one we got. Then we substitute the values and we get the whole answer. Let's try this out. This is not going to be easy now. So from the overall basis that we learned that I is equal to E by R plus R, which we can write it as I R plus I smaller r is equal to E, where V is equal to E minus I small r. That's one thing, and this is one thing. So identical cells in series. First we'll draw the diagram. Cells in series. Here, this is the one. Then I take this, and then this up here, connect it with one resistor here, then this. Alright, so this is E, 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 this is R, 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 this is capital R. I can construct it as N, E, N, R, and this is capital R. So I is technically here E by R plus R, where you can see that E I effective where E effective is NE, R effective is NR, R net is equal to R plus NR. So I is equal to E effective by R plus R, sorry, R net. Let R plus R be R E How am I gonna write this down? You know what? Let's just say that I wrote it like that. So we get Ne by R plus No. So that is one. Different cells in series. Now this one is another case. Ouch! Again. Yes. But we ain't giving up. This is looking great actually. Technically we are doing great. Let me sit normally and different cells in series. Different cells in series. Let's say that let this be it's just why this said. So E1 R1 E2 R2 VXY be E1 minus I R1. Now I should be same, it cannot be divided here. V YZ should be E2 minus IR2. So VXZ is equal to VXY plus VYZ, and that is VXZ is equal to E1 minus IR1 plus E2 minus IR2. That gives VXZ is equal to E1 plus E2 minus I into R1 plus R2. That is overall E effective minus IR effective. Therefore, V exit total we get is E effective minus IR effective. My God. Then the identical cells in parallel. This will take time because this is a really big derivation. Like I'm doing it again. Then we have another derivation which is the last derivation, and then we'll do numericals. Then current electricity is done. I don't know till when this will take place, but I'm gonna give only 2 hours timeline for numericals. I'm not gonna give more time for numericals. However, numericals are really important. I'll choose some of the numericals and we'll practice them. However, I should be practicing more and more numericals so that I can achieve much better ways of doing it, but still, we'll practice numericals. Right. 1 by r effective here, 1 by r1, 1 by r plus 1 by r plus 1 by r dot 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 plus 1 by r will give us n by r. So that's one thing. So r effective is equal to r by n. One thing that we learned. So r net is equal to r by n plus r, which is r plus rn by n. E is remaining same. So I is equal to E by R plus R, right? So but here in the case of parallel, the R effective parallel effective equals E. So if you try to get I is equal to E effective by R plus R effective, what do you guys say? Which is basically E by R plus small r by n, that is E by R n r plus r by n, that is n E by n r plus r, small r. Now that is also correct way to derive it as far as I know, but one thing about this I want to say about is how are we supposed to write R net? So I is equal to n E by n r plus small r. Oh yeah, yeah. E remains the same, nothing is different here. So that's the thing. Now different cells in parallel. This is the boss level derivation here. Be tough. But don't worry, we have practiced it, so we'll try. We have practiced it once, we have checked it once, so we'll do it once. And then we'll move on to the last derivation. Can't believe that after this derivation there is another one derivation, bro. Like I'm still so frustrated with it. Okay. It's 11:30 now. We have to do a bit fast. And I think I have to do it till 2 o'clock. Because right now I have to log in. We have to complete numericals. And then we have to complete the first and second part chapter. We can do this. We can do this. Afterwards we'll actually do some small revision of derivations, just going through each and every part, so that we get some idea of what we actually did for each derivation. For theory, not now, because I feel like we have not mastered, let's say we have done the theory very well. So I'm gonna go through the derivations after just completing all the derivations all at once. Okay, so first of all, in this case, I'm gonna first this. Stop drawing. Let me draw. Better. I believe that this will be okay. No. Next is man, this one. Okay, so technically, let's say that this is E1, this is R1, this is E2, this is R2. So here E will vary, R will vary, and R2 will vary. So what are we gonna do here? First of all, voltage is same in parallel. So what we're gonna do is, oh yeah, I'm not gonna put it on laptop. It's gonna be not that good. Let's put it here. So V is equal to E1 minus IR1. That's one case. Okay, another one is V is equal to E2 minus IR2. Now in this case, what we can do here is make our own types of, yeah, this one is I1 R1, this is I2 R2. So I did this, so I got it as E1 minus V by R1 is equal to I1, and E2 minus V by R2 is equal to I2. Yeah, this is the one. So I is equal to I1 plus I2, E1 minus V by R1 plus E2 minus V by R2, E1 by R1 minus V by R1 plus E2 by R2 minus V by R2. That is going to be E1 by R1 plus E2 by R2 minus V1 by R1 plus 1 by R2. So I is equal to E1 by R1 plus E2 by R2 and minus V1 by R1 plus 1 by R2. Let's see, man. Let's see. So that's why we're not able to solve from here. Interesting. Okay. So I is equal to even R1 by plus. Okay, sorry. That is the first equation. And then I is equal to E effective by R effective minus V effective by R effective. That is I effective. I1 is equal to E1 by minus V by R can also be written as this one. So this is the second equation. Comparing R1 and R2, this is a really complex derivation if I'm being honest. I don't know how human beings were able to solve this. That is crazy, bro. Effective by R effective is equal to where is it? E1 by R1 plus E2 by R2, which gave me E1 R2 plus E2 R1 by R1 R2, and E effective is equal to even R2 plus E2 R1 by R1 R2 into R effective. Now you'll find for R effective, this is the one point, and another one for R effective. So V by R effective is actually equal to V by V into, sorry, V by R1 plus V by R2. So that is technically 1 by R effective 1 by R1 plus 1 by R2. So technically 1, so we get 1 by R effective as, I have to solve this fully, so this is going to be R2 plus R1 by R1 R2, and R effective will be R1 R2 by R2 plus R1. Now this is one idea we get from here. So E effective being E1 R2 plus E2 R1 by R1 R2 into R2 R1 R2 by R2 plus R1. Yeah. What is R effective again? R1 R2 by R2 plus R1. Yeah, because of this. So E effective is equal to even R2 plus, this gets cut off, right? Yeah, my bad. So even R2 plus E2 R1 by R2 plus R1. You know what? R1 plus R2. Finally, bro. Finally, I did this derivation too. We cooked, guys. We finally did it. Now it's the last derivation that remains. We did it. That was a great one. That took me so much time. Literally, like, that took me like more than, like, almost 40 minutes to complete this full thing. Let's do this last one. It's only given here. It's not given in my notebook. I have to check it from here, from my phone. So here, okay, work done by a source. Okay, so it is based on the concept of electrical energy and power, where we know that it is the work done by the electric source to maintain electric current in an electric circuit so that the electric charges have a steady flow is known as electrical energy. And here, first we'll take work done, then work done is equal to QV. Why is it QV? V, let's break this down. V is equal to EL, so QEL. We are cooking. Let's go. So based on this formula, uh, electric energy and power concept. So we all know that W is equal to F into L, F dot L, not N2 cross, not L cross. Let's say that is F dot L, where F is QE dot L and W is equal to QV. Now from here, this is where we can say that Q is equal to I into T, so W is equal to I into T, no, W is equal to VIT. This work done is stored in the form of electrical energy, where E is equal to VIT and V is equal to IR. My legs are paining. Oh shoot. Dang, bro. Sitting on carpet kind of gives me pain. Let me check. Ouch. Ouch, bro. carefully on this one. There's a pattern here too. Like, do you know what I mean? Ouch. Well, let's wait. Let's wait. What is that? It's 29. It's fine. Yeah. Yep. Wait a minute, guys. Just wait a minute. Law of heating effect. That law is also getting proved by this derivation. I just noticed that. I was just looking through the phone. Then what else? Okay. We need power. Power is W by T, which is totally making sense. Yeah. Okay. Okay. Alright, got it. This derivation is easy actually, to be honest. E is equal to IR. E is equal to, why is it I square RT then? Because in VIT, we substitute for IR and then that is from Ohm's law and we get I square RT. This is the 10 standard. For those of you who don't know, this is also 10 standard derivation as far as I remember. In 11th standard, we had like, you know, let's not say anything about it. I mean, we didn't even study anything about electricity in 11th standard unless and until you might have studied something about it in units and dimensions, something about it. But yeah, here in reality, we did not study anything based on electricity in 11th. Physics, by the way. I'm talking about physics, not chemistry. In chemistry, there was some type of ideas like polarity. Oh, oh my god. Wait, so technically we will put this and then we get V by I. What? V is equal to IR. So E. Okay. Now I got it. Now I got it. I got it. Right, let's try doing this work now. Technically, we had done this once. This is not that hard actually. So W is equal to F into L. work done, where if W is equal to QE into L, and W is equal to QV. Now from there, W is equal to V into I into T, and then we can say that work done is stored in the form of electrical energy is stored in the form of electrical energy. There we can say that W is equal to, sorry, E, where this is W, right? So yeah, E is equal to now VIT. Okay, now let's continue from here. Let's say that V is IR, so IR, because V is equal to IR, so Ohm's law, and I into T, which will give us I square RT, that is the Joule's law of heating effect, I square RT. There's another way we can represent this, that is in volts, or let's say in terms of potential difference, potential. So we can write it as E is equal to, there's so many capital E's in this, like capital E represents electric field, then this capital E, the same capital E represents EMF of the cell, and then the same capital E is being used again to represent electrical energy. I think there should be some type of differentiating way to write capital E, bro, because bro, we are getting so much confused in this case. What can we say, guys? Anyways, I square RT, and then you can write it as V square, no, I square, right? So V square by R square into T, R into T, and that is going to give me V square T into V square T by R. So that is also possible. And yeah, I think till there, yeah. This is still the electrical energy. Now talking about power is easier. P is equal to W by T, where P, or we can just write it as E by T. Now from here, let's say I square RT divided by T is equal to I square R, so P is equal to I square R. Or we can write that as P is equal to V square T by R into T, which will give us V square by R. So P is equal to V square by R. So let's take P is equal to I square R here. We'll practice this again, this last derivation, so that we keep it in our mind. Oh, 18 weaves. Oh wait, oh yeah, no change. Okay, P is equal to I square R, right? So I is equal to V by R. No, R is equal to V by I. So I square is equal to V by I, and that will give us Vi. So P is equal to Vi. That is another formula. So we studied this formula, we studied this formula, then we studied the Joule's law of this formula of Joule's law of heating effect. Then we studied about this formula, and yeah, that's it. This is another one, but that's not important. E is equal to VIT. To do this, we come to an end of derivations, but still we'll practice one more time so that we keep it in our brain, and then we'll revise. So this will get completed in under 12 o'clock. So again, W is equal to F dot L, where F is equal to QE dot L, where QE dot L is QV, so Q capital V is equal to W, and then W is where we know that Q is equal to I into capital small t, so V I small t, uh, stored in the form of electrical energy, stored in the electrical energy. I'll switch this off. I don't need this right now. Thank you. Form of electrical energy. Then we'll do numericals. We'll do numericals. Next that we will be doing is numericals. I'm a bit scared for physics numericals class. That's it. I hope we do great. May Allah help us. رب اشرح لي صدري ويسر لي أمري وحلل عقدة من لساني يفقه قولي and رب زدني علما اللهم إني أسألك علما نافعا اللهم لا سهل إلا ما جعلته سهلا وأنت تجعل الحزن إذا شئت سهلا. That one too. I forgot to recite it last time, but no worries. We did it. I did it at the last moment, so yeah, that was fine. Then is stored in the form of electrical energy is equal to VIT. So E is equal to IRIT square RT, okay? And then you can write it as square T by R, no problem, no worries, you can write it as like this too. Then both are possible. Now talking about power, that is equal to W by T, so that is E by T, and talk about this, you can get it as this, get I square R, okay, then E square G by R, that's also okay, so square R, or we'll get P square by R. Alright, we are doing great, guys, let's go. Then last but not the least, if we either substitute the value of I square R with by I, we get VI. So P is basically equal to VI, and that was one such formula that we needed to know. We completed derivations. Let's go. Let's go. We did it. I'm kind of tired, but it's fine. Chat disconnected. Please wait while we try to reconnect to you. Successfully connected. What happened? Really? Didn't see that coming. I'm revising. Okay, I got this one. That's what I got this. Okay. Wait, that happened again twice. What's wrong with the connection? No, I feel like staying awake for a long time, but I cannot do it. Man, we'll see, we'll see. This one is used here. Yeah, this one is used here. Okay. Guys, answer this again. This one we used Q is equal to L by VD. Yeah. This one, yes, we used it. This one where we take VD. That's it actually. And after that, we have this. It's not negative. Not that. This is not negative. Oh, there is a viewer watching me. Hi there, Mo. Hi. There is a viewer watching me. Just notice that. Hi, bro. How are you doing? Anyways, if you don't know what I'm doing, I'm studying physics. So J is equal to NE squared capital E tau. Yeah, that's one new formula we learned. Where NE squared E by M is basically sigma, that is conductivity. So we write it as sigma E. Sorry, NE squared tau by, yeah, that is conductivity. So we write it as, yeah, wait, ml by NA E squared tau, and N by NE squared tau is different. Yes, that's one thing. So J is equal to sigma E. Yeah. J by NE is equal to VD. That's true. That's correct. It's easy. You can directly get the value. Then rho L and E. Only have 2 hours left for numericals part now. That's one thing I've noticed. Only 2 hours left for numericals. So we'll dedicate that only for problem solving, and then we'll end our live stream there, and I will sleep. Tomorrow we'll wake up. I'll start my live stream as soon as possible. We'll be completing the other two chapters of electrostatics with full depth. Not like I'm not gonna write the theory now because it takes so much time. Literally took me 5 hours to complete the theory part. That's crazy. I'm not gonna do that again. Like derivations was fast actually, like 2 3 hours, 3 hours. Yeah, still a lot though. Then overall we'll take some less time for electrostatics now. Complete it as fast as possible. Then we'll do derivations. Then numerical problem solving. Once that's done, if we get enough time, we'll be watching a J lecture of or NEET lecture of the topic of electric flux because I want to practice that, and then we'll do the full fledged practice. Right now we don't have the paper. Once that's there, we'll do it. So for that goal, we need to do it fast. Oh, horse, oh, horse. Hi, man. Hi, I just saw your no. I just saw your chat now. Sorry. I was like, wait, what's going on? Okay. How are you doing, horse? Horse, are you there? Horse. Come on, I know you're there. Come on. Should I respond in chat? Yo, I just saw your chat. I just saw it, man. 1 minute. I don't know whether you're there. It says hi. Wait, let me just. Are you there? No, he left. He left too fast, bro. Oh god. That was under a minute. I sent him it at 12:06. Man, I don't know how I'm gonna like. I should be looking at the chat sometimes. Wait, let it charge more. Twenty-one views. I don't know who was that person who was watching me. I'm sorry, I missed you. I guess. We have completed derivations now. So it's time for numericals. Start from. Kind of wasted my 9 minutes here, but it's fine. Ooh, look at the fence, bro. Oh my god. You know what? I'll take it out. Okay. This should be B. Okay. So this one is I1. C is I2. I3. I'm supposed to thinking that this is I3. I1. This is I2. -4 -10. Yeah, technically, this is going towards -5, right? From ABC to on ACD. Yeah, -3 I1. Yes. I'm gonna put my legs up a bit just to avoid any pain. T plus 3 I1. So it'll be 3 to 0.7. 4. Big, I guess. No problem. So we should be getting I1 is 2, I2 is 2 amperes. Got it. So there we will get 2 plus 2 amperes. Which is I don't know why I didn't write that down. Anyways, so I hope it's not a large value, bro. If it is, then I'm gonna cry out, bro. Hey there, bro. How are you doing? I see a person here. Hi. Uh, Sensitivity of copper and sensitivity of sensitivity of manganese. You guys want me to be creepy? I'll do that for 10 seconds. Yeah, okay, that's it. It's too bright in here. Let me switch off the AC 1 minute. Now we'll lock in. I was here. Okay. Then that's fine. R dash is equal to 9R. Oof. Let me just lower this down so that we get a bit. Yeah. Okay. The steep point is something very distant. Wait. Oh, I forgot to put the charger back. Okay, I'm doing numerical, guys. Overall numericals looks easy. Okay, we can quote current electricity. We're doing great. Um, this is 3.235. Okay, Sooner, I'm gonna end the stream now, man. I'm gonna end the stream sooner, like right now, almost sooner. Getting time. I've been doing the numericals, and I'm getting a bit tired, but then I don't know why. The numericals are easy, but I have to like be really careful with some other calculation mistakes that I'm doing. So yeah. Right, guys, I'm in the stream now. Looks like there are some sounds coming. Guys, the security alert. We have to be prepared now. I can hear the missile sounds. So I'm ending the stream today.